ये नहीं भूलना चाहिए कभी. हाँ, we'll try to judge the next time. ठीक है. Bit slow. Few of the topics went on the fly. Please try to cover limited topic. It was knowledge at once. So, uh, since these topics, the topics being planned for the first week are really foundational one, in which it's almost the most basic things which are available on the internet is something that we are doing. So that is why we have not gone into depth. It was slow because I wanted to bring everyone at the same level. People who are already well versed with the topic might find it a little boring the first week, but going forward, it will be much more challenging and interesting, that's for sure. Second half, the pace was a bit fast. It was not due to time constraint, but the pace was fast because, that's how the entire course progression would be. I would never ever I would basically never ever consider time as a factor. I would always go into depth and would never ever compromise that basically ki time comes, so I would have to wrap things up. That is not going to happen. We'll ensure that every single thing is addressed and in depth. And if you have obviously extra questions, that will be taken at the end of it. Group red holding it covered. I agree. I went a little haywire around the discussions. Like I was not true to the course content or the things that were planned. So, and it obviously happened due to lots of questions being popped up from different topics. Although some of the topics are anyway planned in the future, I should have delegated that. Noted. I'm still learning. This is still my third course, so I'm still learning from that. Expected. Thank you for that. No sir notice, future classes able to tell, and good so far. Chalo. I hope I'll address things will be much better. I'll again share the form link is going to be the same. I do take this feedback very, very seriously. So feel free to add as much as you want there, because this would help us make the experience better for everyone. Chalo. Recording is started. Recording is started. I'll share the screen. I have a very hacky setup right now. Mobile phone is on my laptop screen. Sure. Everything is all set. Caching at various levels. Bata. I won't be contributing anything to this. You guys would have to answer it. Where and what and how will you cache things?
So first, I'd like to start with like layer 7. First would be at the DNS level. Like someone else wants to jump in or
Yeah, Anshul?
Server level, we can have on client also we can have cache.
API server, client side cache. So by client side, you mean on the browser?
Yeah.
Or on the app side, right?
Yeah, on
Okay.
airport.
And what do you mean by API server level caching?
So we can have in-memory cache also and global cache also. Two kind of caches we can have.
No. So API server level is just it, because that global cache would be another category, right? So
Yeah.
in memory. So what Anshul is talking about is having an in-memory cache on your API server. Like for example, when you start your Django server, Flask server, or just Spring Boot something, you can have a very simple hash map, right? Or a very simple dictionary in which you can cache something, so that you can avoid making a database call or a network IO if you already have that information. Typically, this cache could be per request level, per session level, or anywhere. So there are already packages available on all of this framework that gives you a very teeny tiny cache that you can utilize. So which helps you avoid, like for example, if you're building a blog application, getting a blog by ID is something which is a very common operation. Let's say you just have 5 servers running. So, and you have, let's say 500 blocks. So there is a very high chance of people when they're trying to make a call which comes to our API server and it gets so you might want to just cache the blog's response on your API server, and without making a database call or a cache call, you can directly serve it from the memory of your API server. So that is what API server caching is. API server in memory caching. Okay.
Yeah.
What else?
We can store something in DB also pre-computed.
As in how? Give
Like
me a little specific
most
example.
recent blogs. Yeah. So most recent blogs, we can have top blocks corresponding to keywords, specific
Oh,
keyword.
that is still
Uh,
part of use case. There could be one
yeah.
better example than that.
Like something based on warming the content on based on hits.
Warming up the content is still the part of it, but basically where else can you cache it? Malab, basically, what is a definition of cache? It is something that saves an expensive operation.
We can probably do some joins already and like store them as a view or something.
Exactly. That's a great, most underrated, but a great way to do it. Something called as materialized views.
Yeah.
Table views, as in,
Yeah, materialized table views.
yeah, we used to do this. Yeah.
Yeah, great. So
Some-
for folks, if this word sounds new to you, I'm just making a note. Go ahead, Google it on the new tab. All of these techniques are really amazing. Matlab, like for example, in the session that we did yesterday, we were doing that join to basically get the tags. We were doing join from the blocks to block text to tags. Right? You can just create a materialized view out of this thing where everything is already pre-joined and make a call and basically make a query to that so that you can avoid joins. So typically in a read heavy system, this acts as a great optimization. Yeah. Yeah, Anshul, you have anything else to add?
No.
Oh, okay, I'll just lower your hand then. Yeah, something?
Yeah, load balancer level, I guess, like
Load balancers.
L7, L4, or something like that.
So a great example of load balancer level is don't think about like AWS load balancer. Think about if you're having a custom load balancer as an Nginx server or as an HA proxy, you're caching there, right? Because you can have a reverse proxy in terms of Nginx, which acts as your load balancer, obviously. You can cache there, right? So you can configure your caching policies on which, and what load balancers would typically cache is the entire response because that's what they are aware of, right? You can't just cache a certain thing. It will be anything that goes through it is something that it would cache. Okay. Yeah, Anshul?
I'm not sure, like, should we include here this part here or not? Basically, caching on the routing level on the routers, routing paths.
As in actual functional hardware routers.
Yeah, hardware.
It might be a little overkill.
Yeah, as in the packet paths which are being
Yeah.
sent.
Yeah.
Obviously, that is not very relevant.
It
here.
is not really, but it is not really in our hands to do that. Right? So, but if you have your own infrastructure, then definitely yes, you can.
We can have an in-memory cache between the API server in front of the DB, basically.
In front of the DB.
So
as in like your centralized
Right.
cache?
Yeah, like a centralized cache.
Yeah. So with this, basically what implies is if you use an ORM, like if you are using Django, then you can use Django ORM, which has a library called CacheOps. What it does is it makes seamless query. So if you fire a query and if that CacheOps is connected to an in-memory cache, say Redis, and if that Redis already has the output computed for that query, it just simply uses that and it saves the DB query. So it basically transparently sits in front of your database and it decides that whether to forward the SQL query to database or just serve it from the cache. So it operates at SQL table level, but handled on a backend like Redis. So that's what a centralized cache and other transparent cache in front of DB. Transparent cache in front of DB. Example, CacheOps. If you use managed API gateway like Azure API, it also supports request caching. Yes. So caching at API gateway level. What else? Any other technique?
So that CDN will come at DNS level, or it is something different?
No, DNS where you can have separate site caching. So there's a very great experiment running in which one person is maintaining his or her entire blog using pure DNS entries. So he's using the TXT records of DNS to cache things, but we can add CDNs here as well. So CDN side cache. Yeah, Avrancho, you only suggested that.
Yeah, Arpit. So in case of distributed DBs like HBase and all, they also store something like memstore, right?
Hmm.
So aren't they part of cache or something?
Memstore, they act as cache for that database. So this would come under internals of the database. Like for example, how we can, so there's something that we all should learn about is something where your database has its own cache pool. So that's part of internals of database where each of your database has something called as a buffer pool, which acts as your local cache for that system, for that instance of database, and in which it basically caches the page blocks of it basically caches the blocks of the disk which it has recently read, depending on the algorithm that you have decided to apply on that database. For example, if you're buffer, so you can tune your caches, you can tune your database caches and reap out performance. So typically DB buffer pool is something that you can look out for. Okay. One thing that I would like to add here is on API server, almost every single one of us thought about in-memory cache, but on API server, you can also do an on-disk cache. So every API server has some sort of disk attached to it, maybe as small as 8 GB. You can use it as cache. In that case, what you would be doing is you would be saving an expensive operation, which one? Network IO, which goes to the database and fetches the data. So cache is something that saves an expensive operation, not just your disk IO, but also it could be like saving a network IO. So using the disk of your API server that is available to you, you can actually, so basically memory could be like 2 GB big, but your disk is 8 GB. So you can cache a lot of things on the database. And let's say if you're using an SSD, the disk seeks for an SSD and RAM are quite comparable. So you can leverage on disk or your disk attached to your API servers as cache as well.
How this caching is related to memoization that we do at our code level? Is there any relation, or we consider it also as a in-memory thing where we are actually storing the variables, frequently used variables?
This is similar to that, but it depends on what you are caching. So storing it in memory versus storing it on disk. So let's say every request, like in case of our blog, let's say every time you get a block from the database, you compute the response, and instead of and also storing the response on in-memory cache, but writing it onto the disk as a blog ID.json something. And you just check if on disk you have that content, then you return.
Okay, I thought that in memory is in RAM, and whenever the system
Exactly, in memory is in RAM. In memory is in RAM, but RAM is limited.
Okay.
Right? What you can also leverage is on disk cache. But at the end, what we are saving by storing it on disk, what we are saving on is the network operation that goes to the database and fetches the data. Right. And to be really honest, I have used, apart from DNS caching, I've used every single one of them at least one of my projects. So on disk caching of API was a great performance boost while I was working at Practo. In memory, I do here at Unacademy, because otherwise the API phad jata tha. Then obviously client side caching, where we cache the recent queries made by the user on app, and we store last 500 search requests there, so that we serve it from there only. We don't really have to make even a backend API call to that. Then table materialized views, very common, but strangely not a lot of people know about it. Load balancer caching, when you have a central Nginx layer, almost, I've quite heavily used Nginx as my central proxy system, wherein we cache a lot of things. Then comes normal centralized cache that we all use, and transparent cache in front of DB using cache-ops. We are based on Django, so you can have something similar library will be there for every languages. Then API gateway, very recently when we transitioned into microservices with architecture, we have an explicit API gateway which does caching for us. So there we cache some more things. Yeah, Brancho, you have anything to add?
No, sorry, I just forgot to lower
Oh,
the hand.
sure.
Sorry.
Can you give example of API gateway cache and load balancer, like what you used to store here?
आखिरी में लेंगे.
Okay.
Sorry for this, but yeah, आखिरी में लेंगे. 10 टाइम बहुत चले जाएगा. मतलब
Sure.
actually that's a very detailed discussion. That's fine. Okay. Yeah, Srisha.
Hey, so you mentioned on disk or in memory caching, right? So this what you mean is that every virtual machine has some RAM or
And a disk attached to it, right? Some 8 GB, at least 8 GB machine, something. 8
okay,
GB disk. Using basically utilizing that as a cache
and you basically store that in the process objects, like you
in the
create
process objects. Yeah, yeah.
object and then you store it up. Okay, and
Yeah.
what would be a typical example for this?
So something we all have studied during DBMS courses about our printers spool the data whenever it gets the request. It basically spools it on the disk. So what we use it for is to save network IOs. So that 8 GB machine that so the disk that we have attached to the instances, in that we store the serialized objects. Like for example, most popular courses on Unacademy are stored on all the API servers that we have. This is just an example. We use it for something else, but think about it. Like for example, we know that a certain course is going to be accessed a lot, right? And those are like 50, 100 some courses. So the actual response that we send whenever someone makes a get course API hit, that is stored on the disk of that machine, along with on a central cache and on the primary database, right? So instead of our API servers making a call to a central cache and getting the data, we just simply do a disk seek locally, get the data and send it back. So what we are doing is we are saving on the network IO that goes that we have to make a call to that, right? So one network IO to cache, and that cache fetches it from the memory and returns it. So we are saving that network IO from there.
Okay, why not? So a Redis call will hardly take a millisecond or two, right? Or even less than that.
This is microsecond.
Okay, okay. Got it.
And more importantly, it saves one connection.
Sorry.
One less thing to worry about for my Redis.
Okay, okay, okay.
Right. Yeah.
And you mentioned this is a use case that's running in production, or you just gave it as an example?
Running in production.
Okay.
Every single one of these is running it. Well, apart from DNS, because which I've not used heavily, I've just read about it. But every other thing I've used very thoroughly.
And what happens when all the VMs, let's say you have 100 VMs, all of those in-memory caches go stale. So all of those 100 requests at a time, they're made to the backend. And how do you deal? Okay.
So
okay.
we don't have that problem. So again, it is not something that you would always have to do. It depends on the use case, right? For some use case, it might fit very well. For some, it might not. So our data does not go stale for weeks. That is why we are leveraging that.
Understood.
Okay. Chalo. Let's move to the next part. I'll take the questions at the back end of it, Umang. So chalo. Let's jump into today. So today we'll be covering scaling, concurrency, delegation, and the communication. Right. So the other 4 blocks. So scaling, almost everyone knows about it. How do we scale? Scaling is basically your system needs to scale when it needs to handle more requests, right? So when it needs to handle more requests, you need more resources to handle those much requests. So typically, everything is limited. Everything is limited by the capacity of your machine. Or if you have a distributed system, it is limited by the capacity of your infrastructure. So when you get more number of requests simultaneously, that is where the problem that is when the problem starts to kick in. You add more resources to your infrastructure. So there are typically 2 flavors here, vertical scaling and horizontal scaling. Vertical scaling is like building Hulk. You make machines bulkier to handle more loads. Typically what happens is when your API gets a lot of requests, it needs more memory to process those requests, or it needs better CPU to process more requests simultaneously. Right, so this is where you would vertically scale the system, but vertically scaling hits a limit at a certain point. That is where we have another technique called as horizontal scaling. In horizontal scaling, you basically kind of limit your vertical scaling at a certain point, and then you add more such systems or more such components of an infrastructure in parallel, and every one of them is typically identical to handle that much of load. So you can at random pick one and basically forward a request to it. So that's vertical scaling and horizontal scaling. So vertical scaling where you add more CPU, more RAM, more disk to your infrastructure, while in horizontal scaling you add more machines. So a true scaling always occurs when you are horizontally scaling. That is when you are attaining true infinite scalability, because vertical scaling has limitations. After a certain stage, you cannot add more resources to it. But with horizontal scaling, you are free from that limitation. So this is typically scaling out and scaling up. Scaling out may you combine the power of multiple machines. So scaling out is typically what? Scaling out is horizontal scaling and scaling up is vertical scaling. You get better performance because you are combining a lot of smaller machines to get that single thing done. With scaling up, you are limited by the capacity of that one machine. It gives you flexibility, cheaper hardware, but with vertical scaling, once you limit, and obviously with vertical scaling, there is one very interesting catch, which is if your machine is very bulky, and if you are not seeing traffic, then you are just wasting money. Basically, you are basically bleeding money on that resource. So let's say you don't get any traffic during like from night 12 to morning 6. If you don't get traffic, but you have a 64 gigs RAM machine running, so it's like wasting money. So you should ideally scale down and scale up during VRs and handle that. So that is where horizontal scaling gives you that edge where you can just terminate the machine and add machines at will. Deployment is very simple with vertical scaling because you might just have one machine in which code needs to be deployed. With horizontal scaling, you'd have to ensure that there might be a case where a part of your infra is running the old code and other part of the infra is running the newer version of the code. So your deployment always needs to be backward compatible, right? It can never be like, okay, I've just added something that my older code might break, but the newer code would work fine. So there are challenges there, but you'd always have to ensure that your code, your database schema changes, everything is backward compatible. Redundancy, this is a most important one. So with horizontal scaling, there is no single point of failure. This is the biggest mistake that we make, where there are components. Almost every single company has some or the other part of their infrastructure, which is a single point of failure, that if that goes down, it takes everybody with it, right? So that should not how your system should be. With vertical scaling, if you just have one machine serving everything, that becomes a single point of failure. So if that machine crashes, even if we are operating on cloud, like let's say AWS or Azure or GCP, crashes are very common. If you have infrastructure with more than 1,000 machines, you are bound to hear one system crash every single month. That's an average. I've seen more than 3 per week when our infrastructure scaled to 5,000 machines. So this is something that is, we think this is very uncommon, but no, this is very common. So ensuring that, because every single thing that can fail would fail. So think about it. So that's why you should avoid single point of failures in your system. And to do that, the best way to do it is have horizontal scalability. So even if some machines go down, other machines the request can get forwarded to it. They can very well serve those requests. Cost wise, horizontal scaling is cheaper. Vertical scaling is costlier because of the things that we discussed. Like during VRs, it might, so the system is with vertical scaling, the system is scaled to handle the peak load, right? But in most during the most part of our day, you might not get that much of peak load. So that is where you might just be bleeding money on that front, right? So typically, and obviously, as and when the machines get bulkier, the cost of that machine typically goes high. It again depends on the kind of infrastructure that you have, but typically there is this trend where if the machine is bulkier, it is more costly as compared to as compared to equivalent amount of capacity, RAM, and CPU on smaller set of machines. And infinite scalability you get with horizontal scaling and not with vertical scaling. Geo latency optimizations is possible for horizontal scaling, because with vertical scaling, your machine is just restricted to that. Since you have just one machine, it is restricted to that particular region, right? But with horizontal scaling, you can have it distributed across multiple data centers to give you higher availability, right? So there are lots of advantages of doing things horizontal scaling. So by default, this has become a de facto, right? So everyone by default builds system that are horizontally scalable. That is why during any system design discussion, we always have a load balancer and we add at least 3 boxes behind it, right? Which is why it is very easy to comprehend. Horizontal scaling is always better. But if you are building something from scratch, let's say you're building your own product, don't worry about horizontal scaling on day one because you don't have users. So if you are building a feature that is very new, you don't know if it is getting adopted or if your users would love it or not, go with vertical scaling. Don't over engineer on day one. If you're working in a big company where you have massive budget and you want to over engineer from day one, it is company's culture. But typically when you are not sure about the future of your product or future of your feature, then you would always vertically scale up, see things working, and then you can any day it is transitioning from vertical to horizontal is very simple. Transitioning from horizontal to vertical is equally simple, right? So you can anyway change your strategy at will. But when you want to be lean and fast, don't over engineer the complications. Go with vertical scaling till some extent and then add machines to it. So these are something that we already discussed. It's exactly what I've written. The major disadvantage, which is what the important part is, the disadvantage of horizontal scaling is complex architecture, because instead of having just as simple as one machine in your infra, you have many machines. So now when you are deploying the newer version of your code, it has to go to every single one of those machines, which is kind of complicated because some machine might fail, deployment on some machine might fail, or some machine might pass. So you would have to handle those parts. Then comes about licensing fee. If you're using a proprietary software, like let's say if you're using Oracle's database, which is licensed, and if you are horizontally scaling your database, then you would definitely need different licensing key for different parts of your infra. So this goes for if you're using New Relic or Datadog. So they license you for on the servers that you are monitoring. So if you have horizontally scaled system, what would happen is you would have, let's say you have 100 different machines, so you need to buy 100 licenses. But if you just have vertical scaled machine, one machine, you just purchase one license. So that is a disadvantage of scaling horizontally. So if you're using a proprietary software, that becomes expensive when you're horizontally scaled. These decisions are really important when you work in an organization, right? When you're working there, you would make design choices depending on the kind of constraints that you have around, right? So always think about that. Bigger footprint, networking and partitioning. As I said, single point of failure, machine crashes are real, network and partition, all of those errors, everything that we studied during distributed systems course is all real. That all happens in infrastructure all the time. So be ready, make a system robust enough to handle all of this part. A great way, how I perceive horizontal versus vertical, I go vertical at first until a certain limit, and then I transition into horizontal scaling. Because once I go vertical at first, then I'm pretty sure that my feature or my product is always going to work. Like my users want it, my customers do want it, and this product or this feature has longer lifetime. So I know that if it is going to be used, then it makes sense to transition into the better part of my infrastructure, which is basically making it horizontally scalable. So that now that I know that my product is well received, I would have to scale it up once I start to attain growth on it. So that's where I would transition into horizontal scaling and would add more machines to the infrastructure. So that is where I do vertical at first and horizontal later. But again, depending on the kind of organization you are working for, you would always have to think about it. Okay? What should you be picking first? So before I take few questions, let me just quickly wrap this up. So how should we scale our blog, right? So what would we do is if I was the founder of Medium when I just started it off, I would have just started with one massive machine, let it go up to 32 gigs of RAM. And then I know that I've attained product market fit, that people are using my product, then I would have worried about scaling it horizontally. As simple as that. So go for vertical scaling at first and then horizontal scaling. So for horizontal scaling, in most cases, you would need load balancers. So what would load balancer do? Load balancer sits between, so basically load balancer acts as a gate for your infrastructure or basically for your backend API server. So this is that single point of contact that anyone would hit. So all the API requests would come to this load balancer, which internally would forward the request to any of the API servers. It depends on the algorithm which is configured on the load balancer, whether it is round robin, least connections. There are many such algorithms. We will take a very detailed look onto implementation of load balancer, going through the actual code of load balancer in next week, most probably next or next to next week, in which I'll be taking you through the code of a load balancer and how can you write one for yourself. Right. So load balancer is typically, it makes life simple because it gives you that one single point of or one single endpoint to connect to, and internally it has as many API servers as configured, and you can on the fly remove API servers when you don't need them and add more machines when you are seeing a surge of the users. Right. Yeah. Let me take few questions. Yeah, Prabhat.
Yeah, so in horizontal and vertical scaling, initially when we have say like few users, so like when we are scaling, so how does like scaling compare between horizontal and vertical? So like in vertical, if I'm going to increase RAM say from 8 to 32 gigs, or say like if I'm going for horizontal and say I will add say like 3 more VMs to it. So how does it compare like even initially? Like
Initially it would not matter. When you have fewer users, when would you scale? You would scale when you know that either your memory or your disk or your CPU is becoming the bottleneck. Right. For example, you are getting a lot more users are making a request to your API calls and your API, and now you are unable to handle that load because of limitations of your machine. If you know that, then you'd scale. Right. So you'd have those monitoring in place where you would continuously monitor your memory usage, your CPU usage, your disk usage. Right. When you're monitoring that, you would definitely come to know, oh, my memory is slow and my memory is always being consumed above 90%. So I have to scale up the RAM of my machine. That is where instead of using a VM with 8 GB RAM, you would scale it up to 16 GB first.
Okay.
Right. And then if you're trying to do it with horizontal scaling, because that's when you know that it is now limited by that machine. So let me split the traffic between the two. So now that you know that the number of traffic that you got became 2x and your one machine could handle, let's say 100 requests per minute, but now you're getting 200 requests per minute. So what you need to do, you need to add another traffic. So 50% of requests would go here, 50% of requests would go here. Right. So that is why you, that is how you can handle those much of load. And that is where you do horizontal scaling. Clear?
Yep.
Yeah, Varun?
Yeah, actually, it was related to the similar question. My only thing is, how we actually decide that, okay, this much configuration is going to handle these one. Is there any kind of metrics that we have?
No, there is no textbook way of doing it. You would have to monitor it. You would have to monitor. You can do some back of the envelope calculations like you
and
did
here
yesterday.
also there can be two things. Sometimes few of my APIs are CPU intensive. Few of my APIs are memory intensive.
Yes.
And there can be a change in the throughput of the responses.
Yep.
So how
these are challenges.
How do you
These
actually?
Challenges.
Okay.
So how I do it, I'll tell you. So if I have this will add a lot of value to every one of you, because this is something that that for me was a hack, but then I found that there is a better way to do it. So then what I did was I had one Django application which has few APIs that were memory intensive, few APIs that were CPU intensive. What I did was I horizontally scaled the system and I configured my load balancer to forward the CPU intensive to a different set of machine and memory intensive to other set of machines. So I routed, so I basically horizontally balanced across two equally partitioned clusters of my node. So instead of having one homogeneous set of APIs, so I had something like this. This was for memory, this was for memory, this was for memory, and two for CPU. Right. So if you are using AWS, you can have one load balancer and multiple target groups. Right. So there, and similar to this, you on other cloud providers, there would be other things. It is as simple as you being able to identify these. So machines belonging to this target group would serve memory intensive workload. This target group would serve CPU intensive workload. And depending on the kind of URL that I have, right? Because my load balancer only understands URL. Depending on the URL, I'll forward it to a corresponding target group. right? Through this, I can very well manage the workload of, I can ensure that, so I can have these three machines, the top three machines to be of, let's say 32 gigs RAM. Bottom two machines, I can have 16 gigs RAM, but with 16 core CPUs. And here I can just have 8 core CPU. Right. So I can very well manage my infrastructure. So I'll be utilizing my infrastructure to a very great level. Right. I'll be just paying for something that I'm just using. I'm not over provisioning all the machines to have higher CPU. Not all the machines have higher RAM. Right. Yeah.
Okay.
Yeah,
you mentioned your routing API is based on whether it's CPU intensive or IO intensive, right?
Yeah.
How does it actually happen? As in,
on the load balancer side, you can configure any URL that starts with, let's say, my CPU intensive is, let's say, encryption decryption. So let's say anything that starts with /encrypt or something goes to my target group 2, and this is my target group 2.
okay, so you're saying that it actually reads these URLs.
Yeah. So load balancer has access to URLs. You can configure this URL should go to this this URL should go to this target group. If you are using AWS, AWS has AWS load balancers and target groups. So in target groups, you can have some set of machines. So every machine, every EC2 instance will belong to a target group. In load balancer, you can configure a target group to a load balancer. So, and in one load balancer, you can have multiple target groups configured.
Okay, got it.
/encrypt /something, anything that starts with /encrypt can go to my target group 2. And let's say I'm doing a blogs.get. So I have my /blogs endpoint that goes to target group 1. So it will go to these three machines.
Thanks for that. And one more thing is, so you mentioned these API servers horizontally scaling will remove, will add redundancy and remove that. If one of these goes down, everything still comes up, right? But I can also see that this load balancer itself is a single point of failure.
So load balancer is never one machine. It is internally, this is set of machines. This is at least 3 machines.
Okay.
We will go into internals of load balancers in the next week and the coming week, and uske baad wala week.
Got it.
Yeah, how will we have it? But one simple liner for this load balancer, it seems like one machine, but internally it is a set of machines.
Okay, sure, yeah.
Yeah, Umang?
So on load balancer things, will we be going through like layer 7 and layer 4 both?
We'll typically go into, so what I've done is I've implemented a layer 7 load balancer with semantics of layer 4. So I don't read, but when we go through the code, you'll understand how both are implemented. That's for sure. Okay. So I thought of implementing one over other, but then I thought, why should I even read the HTTP request and do something? I just accept raw TCP connection. So I've written a level 7 load balancer with code of level 4 load balancer. So you'll understand both in that.
No, but like this is kind of confusing. If it is a layer 7 load balancer,
you'll come to know that it is very simple to go through. We'll be doing it next week mostly. Okay. One final question before we move on. Yeah, Prabha.
So, like, is there any latency differences between like layer 4 and layer 7 load balancer that we are using here? If suppose we use
that is little out of context, that will take into the class of distributed systems.
Okay, and like another way, like we can implement this CPU intensive and like IO intensive operation differently. Is like we can have like homogeneous API servers at the front end. We use layer 7 load balancer itself to distribute evenly, but like we can have service tiers at the back end. So like we can do our computationally intensive operations. Like we can forward from API servers to some.
You can do that. You can do that. From your API server, you can forward it to any place. You can have different paradigms to do that. No one is stopping you from doing it. This is one of the ways to handle it across same set of machines. So let's say if within that same API code base that you have, if you have two different set of operations, one is CPU intensive, another is memory intensive, then you can have this kind of thing. So this is another architecture. So what we are covering is basically building blocks on how you can even build stuff. right? It's not one concrete answer to a problem. And this is something that acha aisa bhi kuch is possible is something that you should be aware of, right? So basically this is not the only way to implement it. You can take a request from the API server, forward it to a queue, and then consume it on a bigger set of machines. That is another way to do it. So again, with system design, there is no one correct answer. And what we are typically covering is a bunch of building blocks. Yacha, we can build systems like this, we can build systems like that. And then we'll be basically plugging and playing that into various systems. Okay, sure. So this is an interesting question. With horizontal scaling, we now have attained what? We now have attained infinite scale, right? But what is the catch here? What's the problem with we being able to add as many instances to basically add, let's say, 1 million instances behind a load balancer? What could possibly go wrong?
The distribution system is always complex, right?
Mhm.
So the database again would be an issue.
I think
Managing,
shared resources
yeah,
as well as monitoring of different instances, figuring out the failover strategy. I think there can be many issues.
consistency, data consistency
No,
across.
these are just API servers. No? This is just API servers. With horizontal scaling, what we are horizontal. So let's say I'm just adding 1 billion servers behind my load balancer. What would go wrong?
Single point of failure, like if we have single load balancer.
No, load balancer is scaled. It is managed service. Let's assume it is scaling well. That is not a problem. With respect to you as a developer, what could go wrong?
I can see one major issue. So if you add more number of servers, how do you aggregate logs and metrics from them? That also becomes an issue.
No, you let's say you have New Relic configured, which anyway takes input from millions of servers at a single point of time. That is okay. That is still not a concern. There's a much bigger concern. Deployment is simple. Malab, it would just take more time to do it.
After traffic is down.
I'm really happy you guys are thinking in so many different directions. Excellent job. Yeah.
The APIs are accessing data, right? In
Yes.
some or the other way.
Yes.
So that can, be a
Be a
point of
little
view.
more elaborative.
So at the end of it, it's some database itself that is, throwing the result.
Exactly.
So at any
Then-
point in time, you would have to have a locking of row.
अरे यार सही जाते जाते गाड़ी घुमा दी ठीक है
It has to maintain a connection. The database has to maintain a connection.
Yeah,
exactly. So although we can add 1 million machines behind our load balancer, let's say each of those machines make one persistent TCP connection to the database, your database would have to have 1 million connections active at time, which is where we typically, this is a very general problem that we have seen in the industry. People typically add load balancer, add bunch of API machines, but they do not scale their database. But people don't think like scaling up, we will scale up, let's say we are facing load and we have configured a scaling policy that for every 100 requests, you add one machine to your infrastructure. And let's say suddenly you get a surge of requests. Now what would happen is, let's say at a certain stage, you have 1000 machines behind your load balancer. And your database, Bichara, is there, and you have not configured scaling for your database. What would happen? Your database, which is that Bichara teeny tiny machine, and you forgot to scale that up, and that becomes that pain part, and your database goes down because it cannot handle those much of load. It is running 100% CPU, 100% memory, everything is full. Your API service will not be able to make connections to the database because your database is also limited on the number of connections it can create. So this is a major concern. Like for example, there's a very famous deployment strategy in which what people typically do to deploy is this is very famous on the AWS side of things, where if you want to roll out a newer version of your code, what you typically do is you basically deploy the code onto a separate machine, and from that separate machine you configure your you configure your launch configuration, which says that whenever I'm adding a new machine behind a load balancer, what is the configuration I would want to start with? In that launch configuration, you give an image that the newer machine that is added should start with this image. Now this image is something that has code in it. Either it is the older code or the newer code. So during the deployment, what typically happens is you change the launch configuration to have this newer image. And now the policy is applied where it says that double my infrastructure and half it. So what happens is when you scale up your infrastructure twice, so let's say you had 100 machines and you want 100 machines to have a newer version of your code. Initially, you had 100 machines with old version of your code, and you have updated the launch configuration with change of image. So now newer machines that get added will be running the newer version of your code. So what you do is you scale up your infrastructure. So add 100 more machines with newer version of your code. So now at this point of time, you would have 200 machines, 100 machines running old code, 100 machines running the newer code, right? And then you delete, and then you start deleting the instances such that oldest instance first. So the oldest 100 machines will get deleted or will get basically terminated. So then what would be there? You would have 100 machines running the newer version of your code. This is a very common deployment strategy in the industry. The problem with this strategy is when your infrastructure is scaled up to 2x, your database also needs to handle 2x connections. Right. So that is why wherever you see this kind of policies, you would always see that database is always over provisioned. Right. Because if your request load, because during the deployment, your machine, your inventory is anyway going to be 2x. Right. So your database needs to handle those much of connections. Right. So that is why in wherever you will find this kind of deployment strategy, you'll always see that the database is usually over provisioned. Right. So always ensure that your database, so a database in general impact, database cache or any of the shared resources, as it was like very rightly put by someone, where all the shared resources by your API server, be it your database, cache, Elasticsearch, AWS service, any other managed service, all of them are scaled accordingly. Right. So all of this thing needs to support those many concurrent requests. So now comes the next part. How do we ensure, or how do we ensure that our databases scale to handle those many requests? Right. So we saw how do we scale API servers. We saw horizontal scaling, vertical scaling. But what happens with in case of databases? Similar to API servers, with respect to databases, your databases can also have vertical scaling and horizontal scaling. So you can make your database bulkier. So let's say your database was running on a 16 gig machine. You can scale it up and say, I want to have 64 GB of machine. So you can scale up your database to handle more number of simultaneous connections. Right. So you can make your database bulkier. This goes vertical scaling. Another way to do it is horizontal scaling, in which it's kind of horizontal scaling, but in this what we do is we add read replicas to it. In a typical system, the read to write ratio of SQL queries that are fired is 99:1. So for every one write query happening on the database, you would make 99 read queries. Right. So typically what you need to do is you would have an architecture like this, where from your one machine, you would have like, you would keep the machine size intact, but you would create multiple read replicas out of it. So these read replicas are there to only serve read queries, basically selects, no updates, no alter tables, no deletes. So your API server will make connection to one of these read replica to get the answer to your select queries. And all the write requests, so all the updates, deletes, alters, they would go to this master database. So this is typically master worker or master slave database, master slave configuration, where you would have read replica. So now how would the data be synced? So typically if you're using MySQL, there is something called as bin log. If you're using a managed database, they would do it on its own. But every database comes with a way through which you can actually configure a master slave sort of architecture using it. So with Redis, MySQL, Postgres, everyone has this sort of configuration. So let's say when you are starting up server, let's say MySQL D is something, the command that you're running, there are options given to it in which you can configure basically which is the master, am I the slave, you can configure unique IDs and all. Through that, those databases are created with the other database acting as a master, and the data is kept in sync between them. Right. The problem with this architecture though is the replication lag. Right. So let's say your master is taking all the writes. So what is happening is your master had to, so your master did not, so The main advantage we got after creating read replicas is now your master is only worried about taking writes, because reads are being taken care by other databases, right? So at the end, the number of connections being made on the master are very limited. The number of requirements by the master is very simple. It just needs to support updates. Now, once the update is made on the master, this updates needs to propagate to both the read replicas. Let's say in this case, I have two. To both the read replicas, I need to propagate. This is something that is typically done by the database engine, right? The internals of this will be covering in the future section, but this is a very common architecture that you would see when you're building systems. So this is how you would scale your database using master and replica setup. So all the read requests going to the read replicas, while the master is only taking the write requests. These writes slowly get this write slowly gets applied to both of your read replicas, right? So the update command can be fired on read replica, but not by your API server, but internally through bin logs and all, right? There is another way to do this thing, to have an architecture around database to scale up your database basically is using sharded or distributed DB. We will go in which there may be read replicas of each of these database, but instead of having one master wherein all the writes are taken, there is multiple masters. Each database is responsible for its own share of data. Let's say all the blocks written by user one goes to all the blocks written by user one goes to database one, all the blocks written by user two goes to database two, all the blocks written by user three goes to database three, right? So all the three databases are taking in the writes, right? But if you see, we have split the workload into a third, right? So now instead of handling, let's say 1000 connections, each database handles 333 connections, right? So this is sharded distributed database. Details about internals about it, building one, how could we build something that will look in the future part of it. Okay. Yeah, Prabhas.
So like in the second case, the read also goes to all these three, the sharded ones.
In the sharded ones, yeah. So it depends on the architecture. So since the data of a certain user is there only on that one particular database, so the read of that has to go to that database. Any read for that user has to go to that database. Other database to jaan sakta.
And in the first one, can we also have like some kind of partitioning in the master?
If you partition the data, that becomes sharded, na? Partitioning, sharding, same. Okay. Yes, Tisha.
Okay, so I'm not sure if this is a question I should be asking in the following classes or now, but so in these 1 to 3 databases, let's say user 1 makes more writes than user 2, user 3.
We'll cover it again. So the problem which is described here is, let's say one user is very heavy, right? So user 1 is making a lot of writes as compared to user 2 and user 3. So now one of your database would become very hot, right, as compared to the other two. Right? So how would we solve this problem? This is something that is very evident when we build something like an S3. So when we will design S3, we would handle this situation on how do we handle hot partitions. Right? At that time, it will get very clear. Okay. Yeah, Piyush.
Okay, so in the read replicas part, right? So does the DB provide the option to write to the replicas, or do we have to write a script to do that?
Writing to the replica is not done by the API server. Typically, it's read replica. So only read requests go there. The updates that happen on the master, which needs to flow to the replica, it is done automatically by the database engine.
Okay. And in the sharded distributed DB, right? Aggregation of data across different shards.
You can't do that. Right? That's the limitation.
Okay.
So does that mean you can do it, but it's very, very costly.
So does that mean indexes and materialized views won't work on sharded DB then?
Yeah, no. Indexes and materialized view would work so long as, because indexes would be local to a certain database. You can't do cross database queries. Well, joins across databases would not be possible.
Okay.
Yeah, Varun.
Yeah, typically we use connection pooling, right? Whenever we are accessing the database. So ultimately, when the server scales up, You will be having same number of connections.
You would have to change your application level code to handle this well. I hope that answers.
Arpit, do we have a load balancer in front of distributed DB also? Like which one to forward request?
It's typically, there are libraries which take care of this, which decides where to forward to. But typically, it's a very lightweight process that you write in front of, which sits in front of it, which something like a proxy SQL, something sort of thing, which then takes care of, "Acha, this request is for this user, I would be forwarding it to this database."
And a load balancer can also do the same.
But this load balancer is custom, not AWS's load balancer or any managed load balancer which works on HTTP. No, that is not. You will have load balancer, but a generic load balancer. So you would be writing your own load balancer there, where you would say that any request coming for this thing goes to this database. And you can also have another architecture that we'll be discussing next week, where we would have a peer-to-peer network, right? And how to build one. We will do that. Vishal?
Yeah, so Arpit, in the master and the replica setup, right? So here the master would be only one or couple of masters?
To start with, there would be one. If you have multiple masters, this becomes your sharded database. You can have two very similar master, two masters having exact copy of data. That is also possible, which is your active configuration. But in which the problem is you'd have to manage the writes between them. So there is a database configuration which allows active configuration between master, basically multi-master setup. Databases provide that, but it is not recommended. Typically, when companies reach that particular scale, they move to a sharded database, which is much simpler to manage as compared to multi-master setup.
Okay, got it. Because currently we have a master replica, but just I was wondering as to
So typically master is very hard to manage because there are write conflicts. Just imagine having to generate IDs which are unique across databases. It's so hard of a problem to solve. Like having a multi-master setup where you have an auto-incremented ID, because then ID conflicts are possible, right? That's a most simple use case which fails having multi-master setup.
Yeah.
Okay. I'll take one final question and other questions we'll take at the end of the class. Yeah, Branshu.
So Arpit, just quick question that the cons that you have suggested that we cannot do cross DB joins. Is that kind of a limiting factor for not using this?
In most cases, you would never have to do cross database joins. Just think about all the kind of queries that you write. You can anyway model your system such that you can totally avoid cross database joins. In case you have to do cross database joins, it is not impossible to do so. It is possible, but it is expensive. Similar to ACID compliance of MongoDB. It's a pathetic way to do it. But to make it ACID compliant, they would have to have distributed transactions. By the way, something which we'll cover in the next week, how to have distributed transactions. I've actually gone through MongoDB's code to understand how it functions. So we'll go through it. Coming back to this part with the sharded and distributed database. So cross-table joins, if you have a very specific use case about cross-table joins, you can choose to create a separate database in which you are denormalizing the data and storing it to make it available for query. Right. So just basically the data that you require there, you can create a separate copy. Might be a little lag between the system, but you might want to have a separate system handling that. So something like basically flowing the data from this setup into a separate setup and making queries on that. That is much simpler to do.
Makes sense.
Right? Sure. So which strategy should we choose while picking any databases? Do not over optimize. Be at work, be it interview, be it when you're building products, anything. Do not over optimize from day one. Do not over provision, because if you over provision, you are bleeding money. All the points that we discussed for API servers holds very true for database, because API server you can at least downscale. Database you cannot downscale with, because downscaling also takes a lot of time. So you cannot downscale. So if you over provision it, you are basically bleeding money, and obviously not using it, then bleeding money. So typically do sequentially. So whenever it's about scaling databases, go sequentially. Start with a little bit of vertical scaling, then add read replicas, then shard the database. Multi-master setup is possible, but most companies avoid it because now with the advent of with great databases, great NoSQL databases like DynamoDB, MongoDB and all, you get sharding by default and it scales really well. So you typically attune your use cases according to those systems. Right. Sure. Now what do we want? Also, it's 5. Let's take a quick break for 5 minutes and then we go into the other part of it where we talk about delegation, concurrency, and company. Okay, let's take a quick break for 5 minutes. We meet at 5:10, about 8 minutes ka break. Okay, we'll meet back at 5:10. Thanks, guys. it's 5:10. Let's jump into the next part. So now now we change a bit of requirement, and what we say is we want some basic analytics on top of our blog. Let's say how many blogs are there per tag, or how many blogs of a user are there in the system, right? So if we have this kind of requirement, we can typically run aggregation on top of our database, and once we run aggregation on top of our database, we can get some numbers. But in some cases, what we can do is we can delegate the work. So something that we discussed yesterday at the fag end of the lecture, where how do we keep our data in sync from our database to Elasticsearch, right? This is exactly that. So what we do is we are delegating things that we can delegate. So a great line what I heard. So there was a session by VP of Hotstar, and he was explaining how those guys scaled their system during the World Cup final when there were so many people thing. So what he told was they live by this very simple rule: what does not need to be real time should not be done in real time. Anything that you can delegate. So that is what I wrote even yesterday when I was showing you those 6 block sets, where this is the most underrated thing to reap performance out of. So when you want to reap performance out of the system, just think about like the things that you don't need to be done in real time, and if you can skip it or you can delay it, go ahead and do that, right? Because just imagine doing everything in real time, or when I say real time, it's more about in the same request context. So during our API call that comes into our API server, what all things do you need to do there? If you are doing 100 things, and if you wait for those 100 things to finish off and then you return the response, the API responses would shoot really high. So a better way to think about any system is just see the most essential thing that you have to do in the context of your request, and do that, and delegate all other things to workers such that it would be done, but eventually, right? It would not be done in real time in that same request context, but it would be done eventually. So typically what you do is you delegate using message brokers. So SQS, Redis, Kafka, Kinesis, all of these fancy terms that you might have heard of, all of this are part of something called as message broker systems or data streams, something like that, which basically gives you which specifically gives you ability to do PubSub, which is there are some sort of publishers which are publishing the messages to this message brokers, and there are a bunch of subscribers who are reading the messages from this thing. This message queue is acting as it is basically acting as a buffer to hold a message until they are processed by the consumers or the subscribers of it, right? So any example of delegation that we can see over here is like whenever user clicks on something and you want to update the like count on your database, like sorry, it's in the agge slide. So wherever you are, let's say on Instagram, when you hit the like button, the number of likes of the post needs to be increased by 1. Okay, just imagine at the scale of Instagram, if Instagram, instead of doing pre-saved or instead of pre-computing or instead of having a separate field in the database saying total likes count, if it every time a post is rendered, it aggregates the data using SQL query and gets it what's the total number of likes in the database, the system would go down very soon, right? That is not a great way to do it. So typically what would happen is whenever the like happens on the photo ID, there would have been a field called total likes or something, and uska count would have been plus every time that API is called. So I'll basically come to that part. Something like this. So in case of Instagram, let's say that let's say for the blog thing, I want to have how many blogs of a user are there. So instead of running a very massive aggregation behind the scenes every time a user profile is loaded, what if I have a field called total blogs in the schema itself? If I have this field and if I ensure that this field is updated whenever a blog is published or unpublished. So whenever the blog is published, I do a count plus here, and when it is unpublished, I do a count minus here. So I'm saving that expensive aggregation that I would have to do, right? Because aggregations are expensive. for blog, for a very tiny blog is still is okay. But let's say if you're doing it at scale of Instagram where you have millions of likes, let's say Sachin Tendulkar posted a photo, let's say Justin Bieber posted a photo, let's say Selena Gomez posted a photo, or that egg photo that got posted which got the maximum likes, right? So if you do complex aggregations on top of that to see the key, if you do a select count on this on likes table and do that aggregation and get rating, it would be really, really, really slow and it would have a massive impact on your database. So you would want to store such fields pre-computed. So in most cases, your analytics fields are pre-computed, right? So again, going by this rule, what does not need to be done in real time should not be done in real time. You can decide, yes, sir, count updation. I don't need to do aggregations in real time. I can have a small delay. What would happen? I would see count 100 in when there are 150. That's okay, right? A little bit here that especially with YouTube views, they are not real time. They eventually do a count plus plus. They do batch processing and do count plus plus, right? They are not updated in real time. They are not updated on every request, right? So this delegation of work to workers, to asynchronous workers happens through this, right? A typical flow of delegation is your client makes a request. So first client makes the request, then your server does something, and then it submits a task to a broker. This task, and then if you see the server, once it submits the task, it immediately returns to the client. So it immediately returns a response to the client. Array, done. Okay, all good there, right? But independently, what happens is when the task is submitted into the broker, there are a bunch of workers which are running, and these workers consume the messages from this broker, and it behind the scene goes and update the database. Just imagine this updation being updating YouTube views, updating like counts, updating the number of reactions on a Facebook post. Like if it is not in real time, that is still okay, right? But what you would also have to ensure is the lag. So here the key thing is you have to monitor the lag at the time when the message was submitted to the broker and the time it got processed. This lag should be minimal. So while building similar system, while you are adding delegation into a system, what you definitely have to monitor is you would have to monitor the lag. Okay, so you have to monitor the lag and you have to ensure that this is as low as possible. So typically there are alerts placed on such systems where you'd say that any message, if my lag goes beyond 5 minutes, give me a pager duty alert, right? I cannot bear my system to have a lag more than 5 minutes, right? If that is a constraint, it's not 5 minutes a hard rule. It depends on your use case. For some cases, it could be even seconds. For some use cases, it could be hours or days also, right? So depending on the system that you're building, you would have to apply such monitoring rules there, right? So this is exactly what happens. The client makes a request around, right? Now what? Now, what do we do? So now this is where the interesting part lies up. So this message broker is nothing but your queue data structure, right? So SQS is a simple queuing service, or RabbitMQ, MQ is your message queue, right? And the protocol that it works on is AMPQ protocol. So I'm just basically rambling some terms which you can obviously read about. So this is something of a prime importance. So it is basically a bunch of messages being stored in the buffer, waiting for it to be processed. And once it is processed, so now there are queues. Queues are different configurations. So AWS SQS comes in two flavors where you can have a FIFO queue and you can have a normal queue. So a FIFO queue guarantees first in, first out, while a regular SQS queue might see a little out of order messages. So depending on how critical it is for you to see first message first, you would configure your queue, or you would pick a queue depending on your use case, right? On which one would you pick? So a feature that you would need on a queue is expiration, right? Because like, for example, if I'm building a system which sends notifications to a user, let's say I'm working at Practo and I'm building the system and I want to send notification to a patient about his or her appointment. Appointment is at 4 and I have a delay of 1 hour. I pushed a message into the queue at 3:45, expecting it to be processed in 1 minute or so. And the message, when it was processed, it was 4:15. Now, while processing that message, do I have to, send a notification to a user at 4:15 about an appointment that already started at 4? This is a pretty bad user experience. So what such queues would always have feature about is setting an expiry to a message, where you would say that this message, when I'm putting it into a queue, it auto expires at this time, right? Because a message that you delegate, these are some cases. You might have an infinite time of expiration, right? But in some cases, you might want to have a fixed expiration time for a message, where you would say that after this time, this message is not at all relevant. So let it get auto deleted when my consumer is trying to consume it, right? Because I don't want to process it. So either you can discard the message after consuming it and not acting upon it, and just basically consuming it and seeing the expiry kya, and then you discarding the message if needed. Otherwise, it could be offloaded to queue, where your queue takes care ki I will expire the message that you don't want. Then you have at most once delivery, at least once delivery, or exactly once delivery, depending on what semantics you want to play with. And you would wait until message is ready. So there are multiple ways to configure a system. So if you're using a managed broker or managed queue, or you're using an open source alternative, self-managing it, go through all the options which are available, because you might be saving a lot of time rebuilding the things which already come out of the box with these systems, right? Yes, Risha?
Okay, so you mentioned that there are workers who are consuming from the queue, right? In the diagram.
Yeah.
So how does let's say you have 5 tasks and you have 3 workers? How does the queue decide which worker to push it to? Or
it is configurable by the queue. You can say, and obviously all the workers will be identical. So any worker can pick that message. If you want to have affinity to a certain worker, you can configure it if your queue provides that option.
So is it like each of these workers are
Think
sharded?
about round robin.
Round robin, okay.
Well,
And
that's the basic way of understanding it. But typically this acts as a configuration, and you would not want to have a very high affinity for a certain type of message to a certain type of worker. But you can configure it that way if you need.
Okay, got it.
Yeah, Ronak?
So Arpit, whenever you like a post on Instagram, you immediately see that like, let's say like the like was 22 and the like just increased to 23. So is it the case that in my local variable the likes were already stored and it just showed me that 23 is there, but in the backend?
That could happen. That could happen. And most applications do this because it gives you perceived performance, right? So as a user, you are perceiving that, okay, your like got registered. Right. LinkedIn in the year 2015, it was the year 2015 when LinkedIn migrated their entire infrastructure, everything into delegation. They were using Kafka very heavily. So what happened was every single thing was delayed in LinkedIn. Did I say Instagram? No, I meant LinkedIn. So in LinkedIn, they were very heavily using Kafka. So every single one of your action was getting delayed by a lot of time. So your like count got updated immediately when you click, but when you refresh, you would still see the old count, and you see that the post is still liked by you, but the count was old one. That happened as well. So that is where you might choose that, since this is a very critical operation, on my Instagram's post, I might have a column called like count, and I would do ++ in the request context. So my request is not over until I store the like count of the user and update the count into the post variable, into the post table, right? Because here updating the count in the post table is an equivalently important action, correct?
Right.
So you can choose that, but maybe for some different use case, let's say in some cases when a celebrity posts something, this could become an asynchronous job, because that is not really needed. Because if you are not that famous, every single like gives you the dopamine push. Like you would be constantly checking the like, right? And you would not want the like count getting fluctuated like 100, 101, 99, 101, depending on when you refresh, right? So what you would do is you would for an average set of users, or basically for a newer set of users, you might want to have that to be done in the request context. But for some use cases, where for a celebrity, because celebrity never goes and checks the leg count, and even if the leg count fluctuates by 100, it would not matter neither to the celebrity nor to the followers. So in that case, it might become an asynchronous job.
So Arpit, in that case, we have to we have to do it in two ways.
Yeah.
One for celebrities and one for normal users.
Exactly. And Instagram actually does that. Actually, Instagram does that, where they handle massive celebrities differently. They have a separate infrastructure to handle celebrity accounts. They have a separate infrastructure to handle different types of users accounts. So they have segregated the infrastructure like that.
Okay. Thank you.
Yeah, Prabhat.
So Arpit, like what happens when the worker retrieves some task from the broker, and while processing that task, the worker goes down? Like, can we retrieve the same message again from
It
the
depends
broker?
on the queue configuration. If you are using AWS SQS, it especially asks you to delete the messages once you've consumed. If not, then the message might reappear at the front of the queue. So again, this is part of queue configuration. It depends on queue by queue. Some queues give you that ability that unless and until you delete the message from the queue, I would keep on re-showing that message again and again. In some cases, it would say that message retrieved, matlab done. Right. These are all configurations of it.
Is the Twitter blue tick is because of that only for the reasons like
Yeah,
that's
now
the
it is
use case, right?
Yep. Yep. It is very similar to Instagram's notification video, which I discussed. Exact same thing. So when you have that bell icon press and all, this is typically that only. When you have that blue tick, they handle, once you get the blue tick, they would migrate that account to a separate thing and they would handle it differently. Because it is much easier to do that. And obviously that is why they have this very strict rule that you need this much of followers, this much of engagement to be qualified for a blue tick. Yeah, Prabhat?
Nothing, just the same.
Acha. Yes, Risha.
Actually, I just forgot the question. I'll ask you back.
Actually, Umang?
Yeah, so like building infrastructure which caters to different set of users. So is it like the low level implementations differs, or is it incorporated in the same code base which is deployed?
Incorporated in the same code base. Typically, you might have a flag. Like for example, that blue tick is nothing but a flag. Right? If this, then do this. If this, then do this.
So
because you would not want to maintain two code bases for the same.
So like maybe do cloud providers also do that on based on whether you are
Yeah. So do you think AWS would have had so AWS ka biggest customer is Netflix?
Yeah.
Do you think that Netflix would be using the same set of racks jahan pe your application is hosted?
Correct.
Definitely not. Right? They would have a exactly. So
like enterprise paying customers, right?
Yeah. So while I was at Amazon, I worked for a team. We heavily used S3, and we are in overall world. Our team, just my team, was the third biggest customer of S3. We generated 15 petabytes of data every day. Every day, 15 petabytes of data. So whenever we saw a surge in our system, S3 guys would used to call us and say, "Arey, kya ho gaya? Why are you giving this much of load to us?" So they totally separated out our provisions. Our clusters were totally separate from others. So the top 10 customers of S3 have very different racks on their data center. They have actually racks which are quite far apart from each other. Yeah. So that load on one does not really affect in any way to other. That actually happened one time. One server caught fire. I'm not kidding. It actually caught fire. We got a ticket. One of our racks got fired, so your data might be a little slow because it is served from a different availability zone. So that actually happens.
Yeah, even I have faced that because I directly worked on infrastructure. So yeah, and so basically, free accounts which are there for any cloud provider, they do not treat you as the same way or give the same resources like an enterprise account.
Yeah. Yeah, Varun.
I mean, whenever you are saying a message queue, I mean, there are two types of queue, right? There is PubSub and there is task queues, sort of. I mean, I look at SQS as a task queue and Kinesis sort of stuff as a PubSub. I mean, I feel that there was a mix and match. So, okay.
I'm covering that.
Yeah, we can.
Yeah, because if I would have said it in the first thing, a lot of confusion was created. So I just segregated that part because basically PubSub is still PubSub. Anyone is publishing, a lot of folks are subscribing to that same part. Here, with the task queues, the subscriber is always of one homogeneous type. With Kafka, it varies. Right? I'll be covering that.
One more question I had. Batch processing is somewhat different from this, right? From message queues, which we are
Yeah.
doing. Right?
You can leverage message queues to do batch processing, but not the other way. You can leverage any of the infrastructure component to do batch processing. Batch processing is a paradigm. You can use it any way you want. Chalo. Yeah, Kaustubh, final question है इसके बाद में last पे जाएंगे.
Yep. I'm just a bit confused. So, does every subscriber process the message, or
आ
it's
रहा
just one?
है अभी आ रहा है उसी पे आ रहा हूँ. हाँ, चलो ठीक है. So when you have such delegations in place, how does your user interface look like? Like for example, if you're provisioning a virtual machine on your cloud provider, let's say AWS, like the time it takes for the actual AWS to provision that machine might be 5 seconds. Like, and obviously you're not waiting for that. So typically on the interface, you might have an API that polls and checks if the server is provisioned, if the server is provisioned or not. Right. And then it gives you, and it basically once you register the task and it says that, okay, I've taken up the request, it internally would forward the message into a message queue where some of the workers would pick up and actually provision the infrastructure or provision that virtual machine. And it gives you that false sense of completion. Ki, Arey, my task is submitted, my task is done. Now I just need to monitor this status, right? So on typically on the AWS side of things, what would happen is you would see that in progress thing. And then if you refresh, then it would see that, okay, now my machine is available. Right. So typically on your user interface, when you're building this, you might have this thing where whenever you might have a separate API that gives you, like, once your task is submitted, it might give you a task ID or something, and it would poll on the task ID. Okay, what's the status? Is this completed or not? Like, so there are multiple ways of implementing it. This is one of the way. So you might want to build interface depending on how you would want to do it. So with messages queue, there are, as a lot of people you would have figured it out, every one of you knows about it, but chala. So there are two very common implementations of this. So we have message queues and we have data streams. So people typically use PubSub for data stream, but PubSub is equivalently for message queues. Any queue is typically a publisher and subscriber. So with SQS, RabbitMQ, Redis, any of such queues that you have, very interestingly, I've written Redis because Redis can also act as a message queue. That's why I'm explicitly adding it there. If you guys do not know about it, go read about it. Redis has a lot of fantastic functionalities with it. So two very common implementation of this, and this is really important for every one of you to understand, is homogeneous consumers and heterogeneous consumers. So what happens is when you have message queues in which all the messages that go into the queue, the consumers are homogeneous, right? So each of the message can be picked up by any one of the consumer, right? So every message will be delivered to one of this consumer at random, right? So this is typically message queue. As someone rightly called it, is a task queue. So some task needs to be done. There are multiple workers, and any worker can get this message. While there is other type of queue, which is data streams or PubSub, which the most famous implementation of this is Kafka and Kinesis. So here what happens is, instead of having CCC, if you see in the first picture, there is CCC. So these three consumers do the exact same thing. They have the exact same code base thing. They do the exact same thing when they get the message. On the other hand, in the data streams, what happens is the same message can be consumed by multiple consumers, and each consumer reads the message at its own pace. The message is still ordered. So people would always go from right to left. So let's say this is the queue. It's a big storage. Consumers go from right to left. But they consume the message at their own pace. Right here, the consumers in the first thing, when the message queues, your consumers are reading the message from it. Here, in case of Kafka, your consumers, each type of consumer reads the message. So in the first one message was read by one of the consumer and it was deleted. While in the second case, each message is read by one type of consumer, right? So that type of consumer can choose what to do with it. So for example, uh, this example, let's say in my API, I have create block, update block, delete block, and I have two functionality. Right? Let's say upon creation of block, I want to update the count. So I have a count service which updates the count, which does the count plus plus in database. I have another consumer that does Elasticsearch storage to make it available for search. So the same event. So typically when you're designing an event-driven architecture, you would use Kafka Kinesis or something similar, where an event is fired and that event is stored in this event bus. Right? And in this one, this event is consumed by multiple consumers. So the same event of block create is consumed by your count service to make an update of the count in the database. And the same event of block create is consumed by your search service to register that block in the Elasticsearch. This is where this is only possible when you have an event-driven architecture, typically implemented using Kafka or Kinesis. If you were to implement this using message queue, in message queue, what would happen is once the message is read, it assumes that the consumers consuming from the queue are homogeneous. So the message can be at random delivered to any of the consumer. So this kind of thing, that one message block create can either be picked up by count or it could be picked up by search, but not both. If you want to pick it up by both, you would want to have put it into two separate queues for that. One queue for count, one queue for search. You would add the same message into both the queues. Then you can do that. So typically one Kafka Kinesis is equal to multiple queues of SQL. So depending on the type of consumers that you register, where is it? So depending on the type of consumers you register, you are actually or you would be consuming the same message those many times. Each by a different type of consumer. So which means that you are getting a better throughput out of the system, because you don't have to, let's say if you have hundreds of types of consumers in the system, not the consumer, hundreds of types of consumers. Let's say count plus plus consumer, there is one search consumer, there's one analytics consumer, there is one random use case you have, right? So, and you want same event to be consumed multiple times, once by each of this consumer, then you would put it into Kafka Kinesis, right? And other cases, the SQS one, where it's just a simple queue. The message can be picked up by any of the consumer listening to it. So the consumer always listens on the head of the queue. If you see where have I positioned my consumers? In this case, I positioned my consumers at the head. Here, each consumer is reading the things at its own pace. So my consumer is still here. My consumer 3 is very fast. My consumer 3 is just doing count plus plus. Okay. My consumer 1 is very slow because it is storing it in Elasticsearch. So it needs time to get the data from database, basically arrange it in some format and store it in Elasticsearch. Right. So my consumer 1 is slow, which is doing Elasticsearch update. My consumer 3 is fast, whose just job is to do count plus plus in the database. So my consumer 3 is walking very fast. Consumer 1 is slower. And my consumer 2 that does some analytics is here. Right. So every consumer can read the messages at its own pace. Then same message is consumed by multiple people. We will do a very deep dive into Kafka Kinesis and how to use it into future sessions. In case you are not clear, when we discuss other use cases in the future sessions, it will be crystal clear, right? But in the meanwhile, don't you can always go ahead and read the stuff on the internet, right? Okay, so for this thing, when we are doing this analytics of count plus plus, how this fits in our system is on API. On block publish, you are putting one message. So let's say we are using SQS. We are still not using Kafka for this case. Let's say all we want is to do count plus plus and doing it asynchronously for some as an example, right? So we would draft a message and basically put it into SQS queue, and from this queue there would be a bunch of consumers who are consuming from it, whose job is, once the message is consumed, it analyzes for this post and for this user I want to do count plus plus. So it would go to the database, update the entry, right? Typically this is how it would sit. And this is exactly what we discussed yesterday. So what if we want to update the data in Elasticsearch? It would also work on the same set of events, create, update, delete. So instead of copying it at 2 different levels, you can use the Kafka wala thing, right? This is exactly what I've written here. So if we need 2 consumers for the same event, we choose data streams, which is pops up Kafka Kinesis. If one message has to be consumed by homogeneous set of consumers, basically some sort of task queue something, then you would use SQS, RabbitMQ, Redis stuff. Okay. Yeah. Few questions. Yeah, Rana.
Is it fair to say that this concept is of like at least one and at most one? At most one in case of
No. That is different. So that is that. So you can even have at least once, at most once with respect to Kafka as well. You can have it at SQS level as well, right? It is not exactly. It's just basically different types of consumers. So this is not one consumer. This is not just one machine we're talking about. So like my consumers of type count could be 5. My consumers of type this, my search would be 15, for example.
Even in SQS as well?
If for SQS, consumers are homogeneous.
Right. So basically, at least if a message is,
you can configure it for at least once, at most once. So, but SQS guarantees, I think, at least once delivery. Okay. Yeah, Pratva.
So let's say we want to add a feature to a blog, say sending out newsletters of people who follow us. So the task, something like a task queue would be the best fit for it, right?
Yeah.
Compared to having a Kinesis stream for it.
Yes, you can build it using task queue.
Yeah.
Anshul?
Wanted to ask, is it a good idea to, if a message is produced from the same service and consumed by the same service?
Yes.
In order to support.
When you start, yes. But when you scale, no.
Okay.
So if you're building your own product from start, do that. I do that all the time. But once we scale, we would have separate code bases. But there would be some part of code bases that you might have to share. So you can do that. But typically the same or definitely same process cannot consume it. In some cases you might have to do that, but basically no one is stopping you from doing one over other. Right? But you would have to understand the pros and cons of each before you implement. Vishal?
Yeah, so we can have homogeneous consumers for Kafka as well, right? I mean, we can split the data into a single topic can be read by.
Count one is not just one consumer. Internally, it has 5, 6. So these are grouped as one consumer. So you can have different topics and partitions. And for each one of them, you can define my consumer is of this type, and you would be registering it, and that consumers, no matter how many of those processes would run to consume that thing, it would all go one after another. So these are different types of consumers. You can still have, like, you can still register 2 consumers of the same type, but they would consume the messages one after
another.
Yeah. Yeah, Branshu?
Hey, so there is something called push-pull semantics as well, right? The data can be pushed and pulled. So both of this fits up?
Both are pull-based. No one is push-based.
Okay. And which one is push? Is there anything?
No one is push. No one is push. Both will pull the data because there is this one service, one queue, and even the SQS consumers would be pulling from the queue, while even the Kafka one will be pulling. No one is pushing data to the workers. Okay. Final question before we move to the next part. Yes, Krisha.
What would be your negative consequence of this event bus, if there were any?
There are none. Event bus works really well, except if you don't count cost, because event buses are costly. Like if you see billing of Kinesis versus SQS, SQS is per message billing, while Kinesis there is this fixed cost, and then depending on the amount of data that you are putting and consuming. So typically event bus has a very long retention period for messages, typically 14 days. So you pay for that as well. For SQS, it is like jitne message dalo, it stays there for 14 days. You can configure it, but uska pricing is typically per message basis. Kafka Kinesis are a little costly because they need dedicated servers to run for that. And event bus are very high throughput as compared to SQS. So event buses are better options in most cases, a little over engineering, but you can always start. But if you are building a system where you are utilizing it as an event bus, not as a task queue, but as an event bus, then that works really well. If you are using it as a task queue, still okay. Slack uses Kafka as a task queue. No one is stopping you from doing that, right? Might be a little overkill, but works well for most people.
Will we be going into details of Kafka later on?
Not the internals, but where would you use and why and how? We will do that. Like when we design shows, when we design Instagram wall, we'll talk about is Kafka. Why it fits there. But obviously, in the meantime, always Google and read about this kind of stuff. Why this and why that. And specifically in the notification video, I dive deep into like why SQS and why Kafka and what's the limitation of Kafka kinesis and where would you choose to go for SQS versus. If you have not seen that video, all of you, if you're not seen the video, go ahead and do it because that is not something that I'll be covering because it's already out there. You can go ahead and read it. It's taken from my first quote, as is verbatim. Pura. Awesome. Next part, concurrency. So, very recently I wrote a post which got viral on LinkedIn, concurrency versus parallelism. Almost everyone gets confused about this, but typically concurrency and parallelism are interchangeably used. But with respect to this thing, what is concurrency? Concurrency is you being able to execute two jobs at the same time. Oh, sorry, two jobs seemingly during the same time overlap. Like when it comes to parallelism, you are actually executing and making progress on both the tasks at exactly the same time. So typically when you are using a multi-core, when you have a multi-core setup, you will see parallelism. While languages like Python, Node.js are typically concurrent languages, where it gives you that impression because Python due to GIL is just coupled to one CPU core, or it can execute one thread at a time. And this thread are interleaved. So there is a context switch happening, and then the other thread gets a chance, and the other thread gets a chance. So this context switch happening between them, and it gives you the false sense of impression where my processes are running in parallel, but they are not running. So that's what concurrency and parallelism is. Right. So what you would typically do is when you are using languages like Java, C, Golang, it supports parallelism, which means that it utilizes the available CPU cores to the fullest. So let's say if you're running your application onto a CPU onto a 8-core CPU machine, languages like Golang, Python, Golang, C, and Java has this ability to utilize all the 8 cores very well. They have this ability. On the other end, for Python, it is limited by that. Python can just have one thread executing at one time. Right? It can't have it doesn't have parallelism. Although it has threads, but threads are executing concurrently and not parallelly and not parallelly. But basically concurrent is also parallelism, right? So there is slight overlap of definition. When you say concurrent also includes parallelism, but typically people think it into a mutually exclusive way. But by the core definition of it, every concurrent system is every parallel system is also concurrent, but every concurrent system might not be parallel. Right. In general, what you need to take out from this is if your system is multi-threaded, you will be leveraging threading to the fullest when your language supports execution of threads onto multiple cores. Otherwise, it's total waste of time. Right? Because you would not be getting performance and you'd say, I'm adding hundreds and thousands of threads, but it is not doing a great job. Why? Because your language might be restricted. Right? So think before you code. Okay. Achieving concurrency. With respect to this, thread is always the basic unit of CPU utilization. It's a lightweight process. Golang has this very incredible implementation called Go routines. If you have not heard of it, go read about it. It's even lighter than thread, really fast. Golang is the supreme language right now. I heavily code in Go, and it's definitely quite fun to do so. The way you can spin up threads in Golang is easier than any language like ever. It's that simple. But if you're now my question now an interesting part. If your language is concurrent, how will you utilize parallelism on that? So one process is typically stuck to one CPU, right? So you can use multi-processes to take advantage of multiple CPU cores that you have. So that is why for a Django based application or Python application typically runs on top of a UWS GI. server or something similar to that, right? So when you do that, it creates multiple child process of a parent process, each running the same application, sharing the same set of memory, not for the application, but a small set of memory to do the coordination between them. And it basically runs those many processes in parallel. So it utilizes multiple cores by spinning off multiple child processes. So if your language is not utilizing the CPU cores well, you can always do multi-processing and ensure that your language leverages leverages all the CPU cores that you have, right? And this is typically the sync async part, where your sync async programming model. This is somewhat critical to understand. When you do run or when you do execute things in synchronous, you are executing task one after another. When you are doing it in asynchronous way, like Node.js and Python 3's async IO are async in nature, which means they delegate IO operation to an event loop. If this sounds heavy, read about it, right? What is an event loop? There's a great YouTube talk about JSS event loop, which is exactly same as Python. Now languages have a very blurry lines, just like databases. Each one enters into every other's territory. Java is trying to be Python. Python is trying to be Node.js. Node.js trying to be Java by introducing classes, and also everything is blurry right now. So you just need to understand, okay, these are the features that are there. So async event IO, so async IO of Python or Node.js, their IO happens on a separate event loop through which they attain concurrency. They delegate IO operations to that event loop, and then basically every line of Node.js, not every line, but most of the part of Node.js is it is executed asynchronously, right? It runs in the event loop. Because of which it makes Node.js a great language for a heavy IO operation driven or very heavy IO driven workload, right? So you always need to think before you pick any low level language, like which one to choose, why now. There is no one golden answer, but it depends on the kind of resources or the kind of people you have, the expertise. You might not want to choose the best language. Let's say the best language for a certain use case is Golang, but if there is no individual who knows Golang, then what's the use? Because let's say there is just one person who knows, let's say Scala, right? And that person says Scala is the best language to build this part. And what if that person leaves the company the next day, right? You have some code base written in it, you have production running on top of that, and no other person in the company knows Scala, right? That creates the problem. That's why you will choose the language that is accustomed, that is very heavily adopted in your organization, right? But while picking that, you would always need to make that conscious call, like which one to pick, when and what. Okay, a few things before I take questions, Trisha, just give me a minute. A few issues with concurrency: communication between subcomponents, because shared memory model, when you are using threads within that same process, sharing memory is still okay, but when you're doing multiprocessing, let me ask this question. When you're doing multiprocessing, how will the two processes, if they would want to communicate, how will they communicate?
Message queues, or you could have mailboxes.
Mailboxes, huh? Nice.
Like in terms of Android, you could have intents, broadcast, broadcast messages. You could have.
But how does that broadcast work? If there are multiple processes, see, for Android it's still one process.
Shared memory.
Yeah.
Where is that shared memory for multiprocess?
So it could be a simple file open where one process is writing and another process is reading.
Yes, disk. So when you're having multi-processing, disk is what is very easily shareable. You can have one open file on which both parties collaborate. You can take exclusive lock or shared lock on a file and have that communication done. .soc files that you see on if you run an Nginx, have a Python setup or Node.js setup, it creates a .soc file. That is how that is exactly how the communication is happening between the two processes. Like your Nginx gets the request and it gets forward to this. It happens to that open sock file, right? So this is the best way to utilize or to have the communication done between two separate processes. Threads, it's simple. You can have a global variable and you can do that. For multi-process thing, The better way to do it is using disk. Yeah. Intermediate outcomes, depending on the execution path, concurrent use of shared resources like high DB connections, same memory blocks without locks. But locks is something that you would always have to worry about. So when you are doing things concurrently or when you are doing things in parallel, you would always have to ensure that the things that you do are always thread safe, right? Which means that you are either protecting your critical section, like your count plus plus, like let's say two process reading the same variable and both got the old count and both doing count plus plus and updating the value. Now both would eventually write the same value. So even though count should be 2, it is 1, right? Because of this, because you have not applied proper locks in your system. But there is other thing that you can read about is lock-free data structures. I've written some extensive thing on my blog, if you can read about, but we will anyway cover it in this course on how do we handle concurrency at scale, like optimistic locking, pessimistic locking and stuff. We will obviously discuss that. So lock-free data structures is something that you can do that. Conflict-free data structures is also, you can go over, basic both are one and the same thing. You can go about that. Stuff to read about, deadlock and starvation when you're doing things in parallel. Parallel algorithms. These algorithms are specialized to run on multi-core machines. There are special algorithms that are devised. Like for example, if you are doing things parallelly, if you are to give a very specific example, NVIDIA's GPU. So basically, the NVIDIA GPU can be programmed using a language called CUDA, CUDA. So you can have a CUDA SDK on your local if you have an NVIDIA on your local machine. If you have an NVIDIA graphics driver, you can write programs that performs operations in parallel onto those thousands of cores there. So you can go through that. There are really fantastic algorithms to read about. Conflict-free data types, lock-free data structures. You can go and read about it. Persistent data structures is my ultimate favorite. Read about it. You can model time travel using persistent data structures. I'm really fond of them. So there are few very interesting topics that you can read about. I've written articles on most of them. You can read that or do a Google search. You'll find great resources. Few of them we'll try to cover if time permits. Okay. Let's take some question and then we'll move to the final part, which is communication. Yes, Risha?
Hey, I again forgot. I will come back. Because a long.
Yeah, I understand. Okay. Yeah, Chandan?
Yeah, so as you mentioned about languages like Python and JavaScript, right? We cannot actually leverage the multi-threading option. That we use the multi-process. Even we do data work like Node.js child process thing we do.
Yeah.
So do you think like we can achieve the same level of efficiency using the multi-process, like the multi-threaded languages too, like Java and Golang?
You can do that. See. If I talk about pure engineering sense, then definitely not. Right? If you use Golang, it's much faster. If you use Java threads are much faster. Right? Python is slower. Python, Node.js are very slow with when it comes to CPU computations. When it comes to doing things, basically doing heavy work is very slow in these languages. And you can never get the performance that you get out of a Java, or a better option would be Golang, and you can never get that kind of performance. But it is not always about performance. Sometimes if your developers can write code faster, ship features quicker, it's a much bigger win than doing that with highest efficiency. Right. So that's the trade-off. Like yesterday I spoke about Instagram, 3 engineers, 14 million users, 1 year. If they had written that code in Java, it would have taken them 2 years to do that. Right. And Java obviously leaks memory and all. Right. So there are so many ups and downs of this thing. But at some stage, and like let's say you're just about to start building your product, you would always want to optimize for developer productivity. You would always want to optimize the mean time to delivery. Right. And then once you reach a certain stage, like this is exactly same as how we did about vertical and horizontal scaling. For some time you do vertical scaling and then horizontal scaling, right? For some time you would look for high developer productivity, and then you would look for efficiency in the languages. Right. So languages in general won't be able to get performance like Golang or Java in terms of concurrency.
In that question, which language is Instagram written in?
Python.
Okay, got it. I mean backend.
Python.
Django.
Django framework.
Okay, got it.
So always languages might never match the performance, but if they give you higher developer flexibility, productivity, you would always choose it any day.
Yeah, thank you.
Yeah, Pradhan.
So feel free to answer it at the end because it is somewhat to your last point that you put up of when to choose sync versus async, because there are things that you can do in Python, like have a coroutine, do it asynchronously with an event loop. But managing an event, managing asynchronous programming with event loop and having on test with it, like you can easily mess up an async program with a sync program thinking it's doing it in an async manner.
Yes.
So when do you draw that line? So feel free to answer it in the end because
I'll do that. Just do remind me. I have 3 practical examples because I faced this thing so many times.
Yeah.
We'll pick this up.
Okay.
Let's move to the final part of this, communication. Right. Before we start, for the first week, obviously, when I'm trying to bring everyone to the same level, there is no active discussion where I'm putting a lot of questions and you guys are answering. But things will change a lot from the next week. Once I've ensured that everyone is on the same level, then most of the systems is something that you guys would be designing, and I'll just be coordinating around why this and why not that. Okay. So if you think that we are not having a lot of active conversation, just wait for 5 days. From next Saturday, you'll see a very different strategy because that's what usually I do, right? So I just want to ensure that everyone is on the same line. Then we'll start to roll from the next week when we go into database and stuff. Okay. So communication. This is very important. Some random example I took about like TCP versus UDP yesterday, where you think about if you chose a bad protocol for a certain use case and you see, okay, my data is not showing up, it's because that packet got dropped, right? So ensuring that the communication between your components, between your user and your system, and if you have a microservice architecture within that system, is extremely important, right? So there are so many options that you can choose from. So communication decisions determine how different components of a system will communicate with each other. So it from client to server, client to then it becomes client to client via P2P. Like if you're building something like a BitTorrent, it is a pure decentralized system, right? So then the client has to communicate amongst themselves. Your inter-service communication, intra-service communication, because within that service you might have different components. For example, your server to database, you can have it over TCP. There are some databases that accepts UDP connections as well. For example, etcd, you're throwing metrics at it, like you can have UDP configured. Your inter-process communication, intra-process communication. There are so many things to worry about, right? So we'll start to dig into one by one. We'll keep things very simple and see how it goes. Right? We have the usual communication that is very simple. It's like that you have a client, you have a server. The job of the client is client demands something. So from your web browser, it makes an API call. So the client is demanding, give me data of this user. And your server bichara goes to the database, brings in the data, fulfills the request, and then it sends the response, right? And till this point, when this happens, this channel is kept open. So typical this communication comes from HTTP API, REST endpoint. This is the most common way of communication. And in that one TCP connection is formed, and this TCP connection is open until the request is sent and the response is obtained, right? Because if in between the connection breaks, there is no way for server to identify which client and basically how to establish the connection from server to client, right? This is not possible from the server side. So that is where this TCP. So that is why if a request is in flight, which means request is done, response is yet to be sent, and the connection breaks. Let's say your web server died off. You hit a controls and it died off. So your client gets an error, right? Which error it gets? Try it out in case you don't know. Right? Try that thing out. Try to run an HTTP server and see what happens when you have a long-running request and you kill the server. What kind of response do you get, right? And server bichara does all the heavy lifting, goes to the database, pulls in the data, compiles it into a nice looking JSON format, and it sends to the user. And there is an optional timeout when, let's say, your client made a request and your server is heavily loaded and server takes a lot of time to compute that request, right? and there might be an optional timeout configured where your client says that I need response in like 500 milliseconds. Otherwise, otherwise I'll just break the connection. So your connection can be broken from the server side or on the client side. Both way you can configure it, but you can configure an optional timeout to ensure that you are meeting that SLAs, where you are meeting that guarantee that okay, I'll definitely ensure that I'm responding it within this much of time. Another way to do it is using short polling. Short polling is bad idea almost always, but most companies, most products still do it. So the idea behind this is very simple. Your client keeps polling the server, keeps bucking the server every X seconds for any new data. Like an example that we took about provisioning of virtual machine on AWS. Your client might continuously make an HTTP, might make a call to server to say, give me the status of this machine, give me the status of this machine. Here, what server would do is, server would return file. File means empty data, no data. This is very important. It returns either empty data or some data, right? But short polling would immediately respond. Right, so there is something called as long polling as well. We'll come to it. So this is very important to know what is short polling, because we'll be using short polling and other concepts at a lot of variety of places. Okay. So here what would happen is with short polling, your client will continuously bug the server to get the data. The server can choose to respond however it wants, but it has to immediately respond with whatever it has. It's like any general HTTP request response. Like if you are building that AWS console on which you are provisioning that server, you might have a field which gives you the status of that EC2 instance. And once you make that call, it just reads that status and returns it. Makes a call, reads the status and returns it. Right? As simple as that. So whatever the data is there, it would immediately return it. That asynchronous job that is provisioning the machine is updating the same database with, let's say that my server is available. Right, and then the next time it makes the call, it gets available as the status, right? So whatever it has, it immediately returns. This is short polling, right? A great example of this, websites like ClickBuzz or ClickInfo. It does short polling. It repeatedly makes API call to the server, and it gets the response. If it is already rendered those things, it drops the data or reapplies it depending on whatever the logic is, but it does not append it every time. So it makes the call, it gets the data, and it replaces it. If there is no update, it might return you empty data if it's there. So it depends on how you'd want to implement. But the idea, the crux of short polling is very simple. It makes a call and immediately expects a response. Okay, this will be very clear once we look into what long polling is. Right? So with short polling, the possible cons of short polling is like obviously, you are bugging the server every time. So your server will be flooded with a lot of requests, right? Your browser has a limitation. So let's say you have a lot of short polling configured. Your browser has a limitation where it can make only 6 concurrent HTTP requests. And if you have a lot of short polling configured on your client side, your user's bandwidth is like wasting. You are utilizing users' bandwidth, right? So that is obviously not a great idea. So your client has to keep asking server for the data, and a lot of responses are empty. So if your server is configured that way that if there are no updates, I would return an empty response. Then a lot of responses are very redundant, that you already have the data and you are still getting either the same data or the empty data. You're just wasting that much of you are doing too much of to and fro between your client and your server with no necessarily good changes. No big delta is added there, right? So this is not a good idea. So another variant of polling is long polling. Now things would start to make sense. Now what with long polling would happen is, if you see with short polling, there was this file, which means no data, right? But with long polling, your server, your connection is kept open until server has the data. Now imagine if you are building ClickBuzz, okay? And in ClickBuzz, when you are doing that refresh, your client makes a call to a server. Your server waits until it has data, like which means until the ball. Let's say your client has data till the last ball bowled. Let's say over number 19, it has the data. Now until the first ball is bowled, that is 19.1 ball is bowled, this connection is kept open. Your server is waiting for that. Once it gets the data, then it returns it, right? It is not returning the data that it already has. It waits for it. In case of AWS example, imagine that an HTTP API call is made, and in that it is waiting for that EC2 instance to provision, and then it returns the state. So you would never see in progress and do refresh to see what is that. That is long polling, right? If your system is configured this way, where your connection is kept open until the data is available, this is called as long polling. So your server will always respond with the data, with the delta of the data, which is definitely required. And this is not a hard bound anywhere. Just imagine this way where your request, so with short polling, your requests are very short, and you would make a request and get the response, and it would not wait for the thing to get complete. With long polling, it would wait for the thing to get complete and then return the response. Think about this. So the connection is kept open until the data is available. So you would have easily sensed what's the problem with this. It would have too many open connections. So short polling is much efficient. Long polling is not that efficient, because long polling would require the connection to be kept open for a very long time, because unless the data is available, the server is keeping the connections open and not sending in the data. Once the data is available, then the data would be sent to the client. Right? This is very important, because these two are something that is very heavily used across so many systems that we'll be designing. So many. That's why I'm going in this depth to help you guys understand. Yeah, so this is how it would happen. So CRICbus, on the other end, CRICbus, Cricinfo, they are using short polling and not long polling. Obviously, because if you have so many long channels open, what would happen is those many TCP connections needs to be kept open, and your workload on the server would go up. So you would need more machines to scale it. Versus for the short polling, it would make a request, either get empty data or get or basically get the actual data, and then so it's much balancing load as compared to long polling. So this is very important to understand. These are two ways of designing same kind of polling systems. Right now, one case, what would happen when during long polling, because obviously there is some timeout, you can't have a very infinitely long polling setup. What would happen if my connection times out in between that? I would have to establish another thing, and it would wait until the data is available. So let's say it takes like 5 minutes to provision the box. I have a timeout configured for 1 minute. After 1 minute, my connection breaks, and then I would create another connection, and I would wait until my server is available. Then it would again wait for 1 minute, will get connection timeout, then another. On the 5th minute, when my server is provisioned, then I would make a request. At the end of the 5th minute, I would get a response back, yeah, server is available. So I would be making 5 calls. With short polling, I might be making 1 call every 5 seconds. So instead of making 5 HTTP calls, with short polling, I might be making 60 calls, like 12 in each minute. So I'll be making 60 calls once every 5 seconds for a span of 5 minutes to get to finally see that my server is available. Right. So that's the core difference between short polling and long polling. These are not rules that you have to follow. These are paradigms that you can follow. So you can design the same system that requires polling using short polling or long polling, right? And there is another way, third way, and the most famous way that everyone like is thrilled about. We'll use WebSockets, right? So WebSockets is something that has changed the industry, like the way real-time communication happens. A lot of real-time things that you see is running WebSockets behind it. Like when you what happens with WebSocket is WebSockets, just like long polling, are also very expensive, but these are much more expensive than even long polling. Your client and server has a bidirectional channel open. Okay, and this channel is kept open. In this thing, typically what we see, this client makes a request and server sends the response. Here, since the connection is kept open, server can proactively send the data to the client since the channel is kept open. Right, this TCP connection is persisted between the client and the server. So server can send the data to the client can send the data to the server. So it's bi-directional channel. It's different from a typical client server model. Here pe server can also send the data to the client. What is best, and this is why WebSockets are extremely good at, because now what it does is Where it gets advantage over other thing is because in other cases, in short polling and long polling, you would have to do that handshake, your TCP handshake every time you want to set up the HTTP or you want to set up the TCP connection. So that three-way handshake needs to be there. For socket-based connection, for WebSocket-based connection, you don't have to do that. For socket-based connections, you have one time three-way handshake done, and then your connection is persistent. So next time when you exchange the data between basically among the parties, basically client and the server, you don't really have to do any handshake, which makes things very fast, right? But obviously it comes at a cost where your server has to maintain those many active TCP connections with it. It is very expensive to do that, very hard to scale, but it gives the best user experience possible, right? So all the data reaches the client depending on the when the data is available. So this is so now comes the question: what is the best case where I should be using WebSockets? Right. So any place where you have live audience, you have interactions. Like anytime you would have to do real-time data transfer. Like this is where you would use WebSockets. Like updating. Like if you have seen application performance monitoring, like New Relic, Datadog, or some fancy charts. Like in that, WebSockets form a really nice use case where it throws where your server can proactively throw an information at you. Another great example, if you scroll through Twitter and if you're reacting to a certain tweet and at the same time another user is reacting to that tweet, you would see the count getting updated in real time, like the number of retweets or the number of likes getting updated in real time. So any place where this real time changes happen or real time interaction needs to happen, you will use WebSockets. Real time quiz, messages, like if you're building Facebook Messenger, you would use WebSockets to do so. If you are building some examples of IoT, you can build using that. Live classes, you can optionally use WebSockets. There are other ways to do it. But any place where data changes frequently, right? If the data is not changing frequently, you can still do well with short polling or long polling, like CricBus. So for an application like CricBus, where you see live cricket scores, it makes sense to give best user experience using what? WebSockets, because now I can in real time see what the data is updated and I don't, my client doesn't have to do refresh. But if you see the time for the time between two balls getting bowled is close to 2 minutes or 1 minute, right? So for that 1 minute, I don't have this expensive socket connection open, because for that 1 minute, this socket connection is totally sitting idle and just hogging up my server resources, right? So that is not a very efficient use of it. So that is why websites like Cricinfo and CricBus are still using, what? They're still using short polling or long polling, right? And they are not using WebSockets because WebSockets are very expensive to do that. But if you're building messaging application, imagine like once every 5 seconds, your front end is making call to get updates from the other party. And you are seeing, and then basically once every 5 seconds, you suddenly see 5 messages coming, right? This is very poor user experience. So that is where for building messaging apps, WebSockets works really well. So anytime where the data changes frequently and there is real-time communication happening, you would choose WebSockets, right? So in this use case of ours, how will our client talk to our server? For our blog use case, it's very simple, HTTP REST. We don't really need to use WebSockets. But where would we use WebSockets? Now, let's say if you are building Medium, right? And I would really, I've written again, and I would really want you guys to try this out. You can use a library called Socket.io in case you're not aware. Use Socket.io to build this very simple application. It's very simple. So what you can do is on a blog, let's say we're building Medium, and on Medium you have Claps ka button. What if you want to make this button real time? Which means that if there are two readers and one of them claps an article and the other reader is also viewing that page, that other reader could see the clap count getting updated in real time, right? Try to build this. So this is with our blog. Let's say if I want to build this use case where I see the number of likes on the blog to be updated in real time, when some other reader doing a like, this reader also sees that like, I have to use something like a WebSocket, right? So when a new like is registered, I'd have to broadcast my like to all the readers of that page, right? Just instead of having one page, imagine having imagine having 10 pages, Like, so depending on the user reading which article, you would be broadcasting, or your server would be broadcasting the like to those people, right? Just spare some time, think about it, implement a use case like this, because in the next week, what we'll be doing is we'll be seeing how to scale WebSockets. Like, if it comes to scaling WebSockets, we'll actually see how do we scale WebSocket, because this is the most common challenge that comes up when you do it. While we were building live classes at Unacademy, our system heavily uses WebSockets. And when it came to us to scale, we were like really confused, like how do we scale? We just have one Node.js server doing something. Now it comes to scaling, how do we scale this part, right? So the use case is when one user claps an article, the other user reading the same one sees the count getting updated, right? So think about how are we going to build this thing, and also play around a little bit with sockets and stuff. Okay, take few questions. Yeah, Umang?
So WebSockets only cater to one specific data, or in a single WebSocket you can cater to multiple data streams?
You can pass in any data you want, any data. It could be anything. It just imagine it's just a persistent TCP connections between your client and your server.
Yeah,
anything.
So as in all the trading sites and are the best example, I guess, for this type.
Yeah, Rana?
So how is PubSub different than this WebSocket? Like in PubSub, you are just publishing the message and a consumer is consuming it. So if we have a consumer,
this is real-time communication, na? So when that is consuming the message, it is making an API call to read the message, right? And once the message processing is done, that is like another API call to read another message.
Right. If we configure it that a consumer reads it at every 10 seconds, that's like
short polling only. Exactly. So this is something. So if you are building your own SQS queue or you are building your own message broker, your client would be utilizing short polling or long polling. So you have taken a great example. Let's say with respect to a message broker, your short polling would be once the message is read, you make a call to SQS, and if it has any message, it gives you that message. If it doesn't have the message, it would say no message available. That is short polling, right? And what would be the long polling? Your client makes a call to SQS, where SQS says your SQS waits until it receives another message, and then it sends key as here is the message.
Okay.
Right. So that is long polling in terms of SQS. So if you are building your own SQS or your own message broker, your communication paradigm, you can choose to either short poll or long poll, depending on whatever your use case is. Right. But with a few minutes back, someone was saying about the push and pull. WebSockets, if you think about it, WebSockets is push also. Right. So you can configure it for pull as well, but assume that some publisher published a message, and now you want to send this message to all the consumers at once. Like this is possible via WebSockets because you have a persistent connections available. So you can optionally also choose your SQS, so your own SQS, not the actual database, but your own message broker to send this new message, this newly come message to all the consumers. Right. A disadvantage of this would be your consumers might be overwhelmed. It has not even processed the previous message, but it is getting newer message to process. So that's where consumers typically get overwhelmed. That's why push-based models are not a great way to build things. That's why people prefer pull-based models.
Right. And where would you use long pollings, like short polling?
Long polling, I gave an example of SQS. No? So SQS typically use long polling. So if you're using SQS on any message broker, it waits until a message is available. So you can configure the time. You can specify the timeout. You can specify that wait for 15 seconds till you get the message. So if there are no message, wait for 15 seconds. Otherwise, say that no message is available.
Okay.
So there you can wait until that message is available, and then it would return you that message.
Okay.
Yeah, Vishal?
Yeah, so I wanted to know on the walls, Facebook walls, Twitter walls, LinkedIn walls, right? So we keep on scrolling and we get new content, right?
WebSocket.
If WebSocket, right? Just wanted to confirm that. Yeah, so that was.
It can internally make. See, the best way to implement is using WebSocket. They would already have a WebSocket connections open with you. You can implement it via short polling. No one is stopping you from doing that, but that would be a bad usage of users bandwidth, because once every 5 seconds you are making a call to get that information, right? But using WebSockets, you are anyway having a socket connection open. Why not just utilize it and say, okay, new message available?
Okay, so if on the Facebook wall, if I keep on scrolling down,
so you will get like new items in your feed. That the best way to implement is using WebSockets.
But I don't think they implement WebSocket because I never see any socket connection in network tab. Like when you scroll down and it's the end of the list, they poll again for new data.
So see, there are ways to implement it. I'm not saying, if you are building that part, if you already have a socket connection open. So see, what we discussed was you would use Socket.io or you would use WebSockets when your socket connection is not sitting idle. Correct? If your socket connection is sitting idle, which means your one very long persistent TCP connection is sitting idle, and it is an expensive thing to have in your infrastructure that your TCP connection is sitting idle. So if you are multiplexing a lot of interactions over one WebSocket, then you can utilize it. But if you open the network tab, the implementation goes both ways. What Socket.io as a library does for you is it tries to establish a socket connection. If your browser and your server supports WSS protocol, then it uses that. If it does not support it, it falls back to HTTP long polling. So Socket.io, if you're using Socket.io as a library on your front end side and you are unable to create, and your browser does not support WebSockets in any case due to any reason, it falls back to HTTP long polling. Right. So implementation varies. There is no one right way to do it. But if you see Slack, okay, Slack pay, you give reactions. That reactions change instantaneously. Right. So Slack uses WebSockets to communicate. So almost the best example of WebSockets is real-time messaging systems. They heavily use WebSockets.
Okay, so all the WhatsApp and
WhatsApp. WhatsApp, instead of using WebSockets, it uses a persistent TCP connection and a separate protocol called XMPP. And they don't typically use WebSockets. But as a beginner, if you would want to build your own chatter application, you would always start with WebSockets and then migrate to a much complicated protocol like XMPP.
Okay. So in case of video streaming, then I'll be using UDP, right?
No. Video streaming, no, video streaming, yeah.
Live video streaming.
Live video streaming, you will use UDP to send packets, but there would be some packets that you would have to send on TCP. So how we do at Unacademy is we have two separate connections. One that establishes TCP, another that establishes UDP. We have two connections. So we had this hack applied, our turn servers and all. So we will be covering some part of live streaming in week 7, and where I'll go into a bit of depth about it, how that works. But you can build live streaming using WebSockets. It's very easy to build. You can build live streaming using WebSockets. TCP pay drops are very high. UDP pay drops are really high. So it gives very bad user experience. So audio flake. So most probably Skype, I read it, but I'm not sure because it was not an authenticated source. At one of the Twitter feed, I've read that Skype used to use, when it started, it used to use UDP, thinking that it would give the best experience because, you don't really, because it's okay for some of the packets to drop off. But eventually what happened is due to network congestion, a lot of packets were getting dropped. So then Skype moved from UDP to TCP. I read it into a Twitter thread. Not really sure how valid that information is. I've read it about 2.5 weeks back only. So I'm yet to validate that. If someone finds something about it, do share.
Okay. And one last thing. So you use HTTP 2 for all your.
No, 1.1. We are still on 1.1.
Okay.
Uma?
Yeah, so just going back on where we started. So wherever there will be caching in place, either polling or that PubSub model would be mandatory, right? So
no. See, polling is a very different thing. Caching is a very different thing. Okay. You can use cache to make your polling better, but there is no hard couple. You need polling to have cache. If you have cache, you need polling. No, not necessarily.
Cache the data, but the code needs to poll for the data again after some interval, which must be set in the code, right?
So if you have a use case like this, where you in real time you want to update the data which is present in the cache, then you can do that. But typically it always happens upon request. Let's say you are on a web page of a Medium article and you are making a call to that Medium article and getting the likes ka count. And let's say likes ka count is updated in your cache.
Okay.
Once a while you make a call to that and it reads the data from the cache. But no one is stopping you from not hitting it on the cache and hitting it on the database. Right. Okay. And in that case, it is not really needed that you update the like count in real time. You can choose to cache the like count, but not have a polling mechanism where once for the first load of the page, you load the like count and then you don't really poll for any updates. Right. So it is not mandatory to have both go hand in hand.
No, both will be mandatory. Let's say on the Redis layer, right? This was on the web page layer. So on the Redis layer, would that be mandatory? Like, because that is something where actual data is being served.
Why it should be mandatory? As in, who would poll to Redis? Your API server?
Basically, on the same thing about the likes, I refresh the article, I get the new updated count of the data. So until and unless that server API server gets the response from the backend database, which has the updated rights, will never give me the updated output on my
front end, right? Yes. Here, acha, you are saying that cache needs to poll the database to get the updated value.
Correct. Yeah.
No. That's not how it functions, because that would be a very suboptimal way to implement things. Right. So what typically happens is whenever you are caching something, every cache item will have a TTL attached to it, a time to leave.
Yeah.
So once that is down, your entry would not be there in the cache. So it would go to the database, get the data, update it in the cache, and put it and serve it.
Yeah, that's what basically TTL does not correlate with polling, or does it?
No, it does not. So polling is very different. Polling is so with polling, what you are actually expecting is to have a separate thread whose job is to keep the data in sync between your database and cache.
And by TTL, I'm just specifying the code that after this much time, just get the new data.
No. It's implementation when you can say if your requirement is like that, I need the updated data after some time, you can have that. It is not mandatory. It is not at all mandatory to have that kind of check. Okay, right? Yeah. That you have to pull the data after a certain time. Right? With TTL, what happens is, like, let's say you are using Redis on a key, let's say you have a key K and you have a value V set into it. And every time you make an API call, you get the value of K from the cache. Okay, if the value is not there in the cache, you go to the database and get the value. Okay, now every time the HTTP request is something that you are making here, and it goes to that system, it goes to the cache. In case that value is not there, it would go to the database, get the value, fill the cache, and return. Okay, here there is no mandate to keep the data between your database and your cache to be in sync. Your TTL, once after 5 minutes, let's say you have added a TTL of 5 minutes, the entry from the cache would be deleted.
Got it. But it is
next time, it is not there, it would go to the database.
Got it.
Right?
Okay.
This is Uma? Varun?
When you say broadcast in WebSocket, you have to send it to one by one, right? It's not actually a broadcast. It's a, you have to send it.
Great question. Yes, we have to send it one by one. Yes, we would have to do it one by one. We actually iterate through all the open connections and then send. Typically, this is handled by the library through its internal. So Socket.io internally does apply that loop, but it would iterate onto all the open socket connections and fire, send. Yeah, Kaustav?
So in like your practical experience, so how many concurrent users can be long polling a server?
There is no textbook answer for this. Like it typically depends on the use case that you have. Like I have one server on which 10,000 users long poll, right? But a typical hard limit on a number of TCP connections or number of connections on a certain server is close to 65,000. You can have at max 65,000 concurrent connections open on any server. So that's a hard limit on any server.
And this must apply to WebSockets as well, right?
Yeah, because WebSocket is also TCP connected.
Yeah, makes sense.
On that part, like server do not have 65,000 limitation, right? Because I read a WhatsApp blog, they had 1 million plus or something of that sort TCP
But they are not concurrent. They spool the connection.
Okay, but I thought from what I read, they mentioned concurrent exactly because they mentioned the output by logging into the server.
No, that's a hard limit. You can't, but you can't but this is on a single port. Yeah, on a single port, you cannot have more than 65K.
Yeah, I understand, understood that, but even I was reading a Stack Overflow thread around it. It mentioned that client can have a maximum of 65,356 connections, but the server does not have that limit because
Please share that, huh? because I tried creating it on server and I was unable to do so. That's where I was
so
like
you
very
can
sure
tweak,
it is not possible. Please share that.
for that you have to tweak the internal server settings, and that can be done. And WhatsApp has done it. So yeah, they've shared one of the
And that's what I was reading on Stack Overflow. Like
they are using.
Please share that. Now, please share that. Malab, even actually, I tried that just to validate that how many connections or how many connections I can make, and I was stuck at just 65K. So that's what I thought. So please do share that. I would definitely like to go through it.
Stack Overflow thread they mentioned basically server like the destination port is always 80, right? In general.
Yeah.
So a single client can have at max 65,356 connection. Theoretically, we're talking about. But it can go up to 1 million also on a single server box.
How exactly?
Yeah, I did not read. Like
please actually share it on the Discord now. I would definitely love to go through it because like maza aata, I actually tried it on my local machine and it stopped after that time. So then basically that was all my understanding. One server can go at max till 65K.
Yeah, it's a 1-to-1 limit. I mean, let's say you have two servers. The maximum number of connections between those two servers is 65,000 theoretically. It's on the same port.
Is it?
Basically, like a connection is like a client IP, client port, server IP, server port tuple, right? So a client has the same IP for a server, but there's 65K ports available. That's why if you try to make a connection between the same two machines, you would hit limitations at 65K.
So client so from a single client to that's where I hit that limit of 65K.
But there are like a million different WhatsApp clients which are connecting to the same server.
Okay, thanks for the clarification, Kaustubh and Umang. Yeah.
So what you guys are saying is that there is a file for every IP and port combination. So that way you can have more connections from different clients is what you're saying, right?
Yeah, so you can have like 65K connections at max per client. But I mean, there must be some practical limit. The OS must be hitting way before that.
I've just shared the WhatsApp link, and they did it in 2011.
Yeah, and WhatsApp kind of used Erlang for their implementation for this.
Yeah.
So that
WhatsApp
uses Erlang use case.
Okay, so once again, I'm so sorry. So basically on, let's say, server X and Y are communicating. On X, there is a file saying from IP, Y's IP and this port, I have one connection. So I'm going to read from this file always. So that's basically the socket file. And now from Y, there is another connection to a different port. So there will be one more file is what you mean, right? And each file can handle how many such connections? Or what exactly are you guys saying?
So basically, just to assume you make a like request to google.com and there is, let's assume just one server serving for google.com. So your browser automatically assigns you one port as the source port and sends the request to port 80. So server sees the port on which the request came so that like the response can be forwarded to that port. So if there are, let's say 1 million clients requesting for google.com, everyone would be requesting on port 80. Destination port for each of them would be 80, but source port would be different based on based on the IP addresses of all the 1 million clients.
Then it would still be maximum of 65K.
No, but why would it be? Because the IP address is different, right? For each
The
and
IP address is different for each.
so there are two mappings on this IP address and the port for that particular IP address.
Yeah, 1 second. I get that, but on a file server, on a server, right? The number of files you can open for per like as a socket, right? It has a limit. But unless you're saying that a single socket, which is a file on the server, can handle more than one connection, in that case, you can reach that 1 million. But I'm not sure how that
Yeah,
works.
basically
correctly.
as in they must have modified on OS level some tweaked some things. But
Okay.
You can change the maximum number of file opens allowed using ulimit -a. That's for sure. You can tweak that, but not sure what the max limit of that is.
This was mostly around
Yeah.
TCP connections. How many TCP connections can be opened on a single server? So that does not has any limitation. Obviously, might be the server gets killed. You'll have to modify the code base and like the internals of the
I
OS.
think-
I'm not aware about those things.
Yeah, I think it comes down to how many concurrent users can contact the server rather than the number of connections, right? Then it becomes like 1 million concurrent users can actually talk to the server, not the number of connections. Number of connections will be way lower than that, I believe.
No, number of connections will be actually that much because WhatsApp in their blog, like if you search, they posted the actual stats using like NetStat.
Link डालो ना यार सब पढ़ते बहुत मस्त है.
Yeah, I've pasted the link. Yeah, I've given the link in the Discord. Yeah.
So I even actually tried and logging into server and seeing how many connections are there. So it fluctuates and goes well beyond in that limit on a highly loaded server.
Yeah. So Arpit, what is the scale that you guys have dealt?
We never crossed 65K. We are just per server 50K connections because we never let our servers go past that because even we had that understanding is 65K is the limit. This if actually this is true, this actually changes the game for us.
Okay.
Okay. Yeah, Pradman.
So coming back to my original question, like where do you draw the line between sync and async? Because technically you can write coroutines, right? Avoid those locks and deal with those coroutines and event loop, which eventually would drop down your developer efficiency because testing async code is much harder than synchronous code.
That is why there are no adoption for Python async IO.
Technically there are being a Python.
Good folks do write it, but maximum companies have not adopted it.
Yeah, only people who have like core Python developers or core Django developers do it. But that's how Instagram scaled.
Yeah.
Basically, because they hired all the core Django developers, so they don't have to deal with their Django limitations and they can carve out the pieces of Django itself.
Yep.
One case of async IO with Python I basically saw was to use containers along with it. Like, so basically you
which type of container?
A Docker container. You deploy a Docker container and that has the entry point to the async processes, async code of the file, something of that sort. I did not understand fully the code base, but it was something of that sort, deploying the container every time, and that does handle that.
So, Arpit, you were telling about like your 3 experiences, I guess, if I remember correctly.
Acha, about the sync async, na?
Yeah.
So we just migrated we just started a new code base with Python 3. He said, "Chalo, let's use async IO, AIO, HTTP, AIO file, all the file IOs to be async to get performance." First week, we did everything async. And then a fresher joined the team and he messed up the entire production. Entire production got messed up because we thought, because he said that he knew async IO. Like and again, like you said, it is very hard to catch bugs with async code. It's really hard to catch a code.
You can easily mess up an async code thinking it's asynchronous.
Very easily. And that's what happened. Because this was the first time when we were writing async IO based code, like in Python. And then what happened was when the newer changes got added by a newer developer, and while doing that, while in the code review also, because our natural intuition was like sync, because this was the first time when we were consciously doing async, but still that जो natural kick basically our intuition kicked in. And this looks good. चलो ship करते production में, and it broke the production. Pura values jumbled here and there because all the variables were shared. Values were getting updated. We had an in-memory cache, chota sa value got like really weirdish value there. And we were all wondering what exactly happened. And then suddenly we recalled, array, entire code is async, array, this flaw, array, that flaw. And then what we did was we changed the entire code base. We moved out of async IO and changed this thing. Similar thing happened with Node.js as well, because one of the developer was experienced enough, but has an experience in Java, and he started writing in Node.js, and pura async wala sync ho gaya and messed up. So those things should have been caught during code reviews, but we were just 12-member team then, right? So that is not possible. But now, but if the team size is bigger and people have expertise, then it's easier to do so.
What version of Django do you use? Because
in very old one. So for this one, we didn't write in Java. We wrote it on Fast API.
So it's naturally ASGI rather than WSGI.
Yes.
Django 3 also comes with ASGI. That's why I wanted to ask.
Like,
if you're into older Django, then you won't get that facility.
Our monolith is like way old. It was created in 2015 and it has never upgraded a version.
That's a lot of security issues you're dealing with.
Yeah, I know. But no one wants to touch that. Chalne do.
It's a lot of tech debt.
Yeah.
So like in production, like it is like a thin line to choose async or not.
Yeah, exactly. If you have resources, if you have engineers who can work upon that, and you have people, more importantly, you have experts enough that who can spot those things, who can spot those intricate details, then go for async IO, because async IO is the best. I wrote, for me to understand async IO, I wrote one downloader wherein I downloaded PDF files. I wanted to read a lot of research papers regarding Wikipedia. So I downloaded a bunch of PDF files from ARXIV, Wali website, and I was doing it with Python request. It took me 2 hours. When I moved my code to async IO, it took me 3 minutes to download all of those files. And basically that's when I realized how great async IO is.
Okay, and also depends, like if you are making the code extensible, like if someone new joins and like
that's thoda sa mushkil ho jata hai, yeah. And especially when the fresher joins, because he or she might not know a lot of details. So then onboarding them takes a lot of time. It's not that for them it is hard to comprehend.
Yeah.
It's that for them to get onboarded into such paradigm might take a little longer than expected, right? Especially when we were a very lean team, like 12-15 member strong, so far like we don't really want to take those things. Jaane do, baad mein dekhenge. Now that we are 150 members strong, top kar sakte hain.
Also, having such service like file downloader is basically a toy app.
Exactly, it's a toy app. Yeah.
So dealing with production issues is kind of difficult in async rather than building toy apps with async.
No. So what typically happens here is you try to move such toy apps into a microservice and use async for that. So build a service that deals with just that small thing, which is easy to manage with async IO.
Just divide and conquer basically.
Exactly. Uspe chalta hai wo, uspe mast chalta hai. And basically that's the strategy that we have adopted to have a wider adoption of async IO. To build such toy apps that solve some very specific problem, but it has to use async IO. So धीरे धीरे ना फिर वो culture grow होता है.
Async IO gets used to, like you get used to.
You get used to it. You get used to it. Yeah, it takes time.
As in like using it in real life, incorporating is the main challenge, and understanding where to implement, because I'm also trying to understand, like I know the basics, but how do I incorporate in the current code is the only challenge. Like I'm not able to get past that.
Existing code mein async IO is really hard to like add. People will get confused a lot. So it is always easier to start a newer code base on top of async IO versus add async IO into an existing.
Yeah, basically we wanted to migrate to async IO. So like it has been going. I'm like, it is not mandatory, but I was just thinking around it, but could not get a starting point of.
So if I was the engineering manager of that team, I would have done that. I would have specifically carved out processes that could be run asynchronously into a separate code base, run it into basically run it as a separate service, and slowly migrate the entire code there.
Okay, yeah, I don't have that much experience.
Exactly. क्या करें, थोड़ा
Also,
तेरे
there
ऊपर ही
is
डालना।
one great talk on PyCon US where Lynn Rhodes, she works at Spotify, builds a clone of their service, which was eventually written in Go. She shows how real world async IO applications behave. I can share that talk and
Do
people
that,
can
do
look into it.
that. Feel free to do that. Chalo. Nice. Anything else, anyone?
Yeah, so today we discussed in the beginning of all the different types of caches, right? Based on all the things to do for yesterday, right? So, were there any caches that you still that we might have missed out?
मतलब बाकी बहुत advanced है, मतलब we के मतलब every single one of them is used. See, that count would be 12. I'll just go through the list. पहला वाला 12 is something that I use. 1, 2, 3.
I guess one thing that I'd like to sort of bring up is query caches. Or is the same as a transparent cache?
Transparent cache sitting in between. Example cache ops. So you can go through what actually cache ops does. It basically transparently sits between your API server. Basically, it is part of your API server, sits in front of your database, and it basically uses a central Redis as a storage. Once you fire a SQL query, it sees that if it has already objects that are fetched from that query already there. If it has, it solves that. If it doesn't have, it goes to the database, fills up the cache in it. That's kind of
okay. Got it. And the query cache which I am talking about, which Postgres provides, is like on the machine, where you increase the RAM or NVMe storage, and then you cache the queries there. Like you could sort of common queries are cached there, so they never actually hit those.
Okay, I'll go through it. I just made a note. If you find any great link, do post it here. But otherwise, I'll anyway go through it tonight.
Okay, off the topic, what is this digital whiteboard? I mean,
this thing. This is my iPad on which I'm writing it on an app called GoodNotes.
Okay, fine.
So, Arpit, when we were discussing database architectures, in case of multiple masters, you said that we can have a problem of auto-generated IDs conflict. So, won't we have a similar kind of problem in sharded database architecture or distributed architecture?
But you can have a workaround if it's a sharded database, because your query, the way you'll be doing queries will be very different, right? It will be partitioned. It will be partitioned by a certain partition key. So everything will be running on just one partition. It would never go across partition. So ID would be on that partition key for that ID that way. So for example, so it would never interfere. So that's why partitioning. So basically, partitioning gives you 100% exclusiveness.
Okay.
So that's why there won't be any problem. But it is a bit of challenge to build that thing. If you are using DynamoDB, it demands you to have a partition key, like your hash key.
Yeah.
Right? So it expects you to partition the data from day one.
Thanks.
I want to add a small point to that. So I think I read a blog in Twitter where what happens if you have 100 VMs, they actually have rolling counters on each VM running, which creates a unique ID every time a request comes to the VM. So basically, they shard the request to one of the slots and then add a rolling counter to it so that it never overlaps.
It never interferes. Yeah. We will have a very interesting session about distributed ID generation in distributed systems, week 3rd. उसमें बहुत मजा आएगा. And how different companies have tried to build their ID generators. उसमें we will talk about all of these fancy things. मजा आएगी उसमें. चलो. Anything, anyone? Pradman, your hand is raised. Do you want to add? या पहले का था? नहीं. Awesome. चलो. Thanks a ton, guys. Although it's 7, but it was really fun discussing.
So one more thing off topic, I did figure out why we weren't getting emails. I can send you the screenshot. Or I can share my screen now if you like. I have opened it.
Was that because of
So
that subscribe?
I'll share this. I'll share the screenshot on the Discord channel. Just give me a minute. Upload file. This is not. So if you see the Google group that's associated with this channel, right? This cohort. So you can see on the subscription, no email tag is selected. And then for rest of the groups, I get each email that's posted there. So maybe by default that's removed.
That's the setting. Oh, okay. But this didn't happen with the last cohort.
Might be the issue. Like I was just closing my browser and saw this. This was the only unique one. So might be the issue.
Okay. Okay. I'll just make a note and post it there. Okay. Agar no email hai to, so basically you can change this from no email to each email.
Yes.
Okay. I'll just make a note there.
So Arpit, can you add me in the Discord group?
Yeah. I'm just finding it. I just saw your email. Samarth Varun. What's the name? Wrong guy.
Which one?
Your Discord username. It's Vikas Kumar.
Yeah. So
Find it on welcome. Acha, you have invite on that Discord channel. That email. Usme there is this invite link.
no, I didn't get any invite link in that mail.
Email में आया है. Onto that Google group na. Go to the Google group you are part of. You will see the invite link of Discord. Wait, I'll send it to you. I'll just make a note here. This is very weird. No email wala setting needs to be changed. I'll just send you a link.
Okay.
ठीक है. चलो. Still 25 folks. अच्छा session हुआ लगता है. Nice.
Bye folks.
Yeah, chalo. Thanks guys. See you next week. I'll put out agenda tomorrow morning.
Thanks, Arpit. See you.
Yeah. Bye. Thanks guys.